Look up tonight. See that quiet scattering of stars? That faint smear of light we call the Milky Way? It feels empty, doesn't it? Sparse. Peaceful. Like you're staring into the loneliest place in existence. Here's the truth, that emptiness is a lie, and it's one of the most beautiful lies the universe tells. For centuries we believed it. The night sky looked sparse because, well, it is sparse from where we're standing. We're stuck inside one galaxy, seeing the cosmos through a keyhole, and our brains just accept what our eyes show us. But then we built better telescopes. And everything changed. Astronomers started pointing instruments at patches of sky that looked like pure nothing, just darkness, void, empty space, and left the shutter open for days. When the images came back, thousands of galaxies. Hiding in what we swore was emptiness. Stacked on top of each other like a cosmic traffic jam. That's when the question hit. How many galaxies are actually out there? Sounds simple, right? Just count them. Except we can't. Every time we try, we hit walls. Light that's been travelling for billions of years, stretched and faded by expanding space. Galaxies so distant we can't even see them. We have to guess they exist based on math and simulations. The deeper we look, the more we find. Fainter ones, smaller ones. And the number keeps changing because we keep finding more. The universe doesn't want to be counted. It reveals itself in layers, giving us just enough to keep searching, but never quite enough to finish. So this isn't about me giving you the answer. There isn't one. Not yet. Maybe not ever. This is about how astronomers even begin to tackle something this impossible, how they use nearby galaxies to understand distant ones, how deep field images and supercomputer simulations slowly build a picture that's always evolving, always incomplete. The universe loves keeping us guessing. If you're into mysteries that don't have easy answers, the kind that make you think, hit that like button and subscribe. This channel's all about sitting with the big questions instead of rushing past them. Quick question. Where are you watching from? City lights drowning out your stars? Or somewhere dark enough to actually see the Milky Way? Drop a comment, I read every single one. All right, let's figure out how we even start counting the uncountable. There is only one galaxy we can ever experience from the inside, just one. Every other galaxy in the universe appears to us as a distant object, a patch of light set against the dark. But this one, our Milky Way, surrounds us completely. It cradles us. We are embedded within it, like a single cell within a vast swirling body. Look up on a clear, dark night and you see its evidence in every direction. Stars, countless stars, pinpricks of light in a deep velvet black. Dark lanes of cosmic dust, obscuring the richer light behind them, creating rivers of shadow across the heavens. And that faint, ethereal band of glowing haze arcing overhead, the dense disk of the Milky Way seen from within its own plane. This position feels intimate, it feels familiar, it is our home. Yet this very intimacy, quietly, very profoundly distorts our perception in ways that are easy to overlook and hard to correct. From the inside, symmetry is impossible to judge with certainty. Scale is fiendishly difficult to measure. Completeness? It's almost impossible to even define. We have no external vantage point. No way to step outside and look back to see the full spiral structure laid out before us. Instead, we must reconstruct our own galaxy indirectly, piece by piece, star by star, region by region. We use distance estimates, measurements of motion, and assessments of brightness as our guides, and they are imperfect guides, every one of them. This fundamental challenge shaped the earliest, most earnest attempts to understand what kind of place we actually live in. At the dawn of the 20th century, astronomers attempted to map the Milky Way by the most straightforward method they could conceive, counting stars. They pointed their telescopes in different directions and tallied the points of light, assuming that where they saw more stars, the galaxy extended farther. One of the most influential efforts was led by Jacobus Kapteyn. With immense patience, he and his collaborators assembled one of the first systematic models of our galaxy, using these star counts and assumptions about how brightness was distributed. The model he produced was elegant, mathematical, and satisfying. It suggested a modest flattened system, a kind of cosmic disk, with the sun located reassuringly near its centre. It was a galaxy that felt knowable, contained, and it was deeply, fundamentally wrong. The error wasn't born of carelessness or lack of rigour, and it was born of invisibility. Kapteyn could not see and could not properly account for interstellar dust. This fine, dark fog fills the plane of the galaxy, especially where stars are most densely packed. It absorbs and scatters light, silently erasing the light of distant stars. To Kapteyn, those distant regions appeared dimmer, not because stars were scarce, but because their light was being stolen along the line of sight. With no way to correct for this, his map showed a Milky Way that was smaller, neater, and more complete than reality. It was a galaxy that ended where our sightlines grew murky. This early mistake matters, not as a critique, but as a revelation of a deeper, repeating pattern. When our observation depends entirely on light, absence can masquerade as emptiness. What we do not see may still exist in vast numbers, and hidden behind a veil we didn't know was there. That lesson, learned painfully at home, echoes through every later attempt to count galaxies beyond our own. It is the first whisper of cosmic humility. As techniques improved, astronomy began to listen to a different signal. Not just where stars were, but how they moved. Stellar motion offered a different kind of information, one less vulnerable to the whims of dust and dimming. By tracking how fast stars orbited the galactic centre at different distances, it became possible to infer the galaxy's hidden architecture, to weigh it, to understand how its mass was distributed. This is where rotation curves enter the story. A deceptively simple graph that would upend our understanding. When you plot the orbital speed of stars against their distance from the galactic centre, classical physics predicts a clear pattern. Beyond the region containing most of the visible mass, the bright bulge and disk, the speeds should fall off like planets in our solar system slowing as they orbit farther from the sun. But the universe, as it often does, had other ideas. Observations showed something unexpected, then inexplicable. Stars far out in the galactic suburbs were moving just as fast as those closer to the downtown core. The galaxy was behaving as if it contained far more mass than could be accounted for by all the stars, gas and dust we could see. It was acting like a much larger, heavier object. Vera Rubin's meticulous, relentless measurements of galaxy rotation curves made this discrepancy impossible to ignore, to explain away. The implication was not a minor correction to a model, and it was a structural revision of reality. A galaxy was no longer just the sum of its luminous parts. It was now understood to be embedded within a vast, massive halo of something unseen. This dark matter extended far beyond the edges of the luminous disk, a ghostly gravitational skeleton holding the bright flesh of stars in place. This changed forever what it meant for something to qualify as a galaxy. A galaxy was not defined solely by light. It was defined by gravitational coherence, by the presence of a massive structure, seen or unseen, turned capable of binding stars together across billions of years. Suddenly, the visible portion, the part that paints the night sky, became merely a tracer, a luminous symptom of a deeper, darker condition. From inside the Milky Way, this realization complicates everything. The bright spiral arms that dominate our night sky, the ones we draw in textbooks and dream about, represent only a fraction of the system's true size and mass. Surrounding them is that immense dark matter halo stretching several times farther than the visible disk. And embedded within that halo are other structures, ancient globular clusters, fossilized streams of stars torn from smaller galaxies long ago, and satellite galaxies so faint they barely register against the stellar background. If the full, true extent of our own home cannot be seen directly from within, then any attempt to use the Milky Way as a template, as a standard ruler for understanding other galaxies, must proceed with immense caution. What appears complete to us may be only a fragment, where what feels typical from our vantage point may be profoundly biased by perspective. The internal uncertainties that accumulate quietly but persistently. Distances to individual stars carry margins of error. Dust is not spread evenly, but in clumps and tendrils. Populations of stars overlap in our line of sight, confusing the picture. Even basic quantities, the galaxy's total stellar mass, its true diameter, are revised, sometimes significantly, as new data arrives from missions that see in different light. Each uncertainty is manageable on its own, but together they form a chorus reminding us that the Milky Way is not a known object in the everyday sense, is not a solved problem, is a model, continuously refined, never finished. This matters deeply when the goal is to extrapolate outward, to use our home as a baseline for the cosmos. And counting galaxies elsewhere relies on a chain of assumptions about what galaxies generally look like, how massive they tend to be, how their emitted light relates to their total mass. If our primary reference point, our home base, is itself only partially understood, then every larger estimate inherits that foundational uncertainty. It builds on shifting sand. There is also a subtler, more psychological issue at play. Living inside a large spiral galaxy normalizes largeness. It makes grand structure feel commonplace. Spiral arms feel like a standard feature because they dominate our nearby views. Dense star fields feel typical because they fill our sky. Yet when the local universe is examined more broadly, a census reveals that massive, glorious spirals like ours are relatively rare. They are the cosmic aristocracy, and by number, and the universe is dominated by smaller galaxies, fainter galaxies, irregular systems that look nothing like the majestic whirlpools of our imagination. These are the common folk, and they're easy to overlook. The Milky Way is not misleading because it is bizarre or unusual. It is misleading because it is prominent. Its brightness, its size, its striking structure command attention in a way that the faint myriad dwarfs do not. From the inside, that prominence can feel like a baseline, a standard issue galaxy. In some respects, it is an outlier. So the very first step in asking how many galaxies exist is not a leap outward into the deep field. It is a turn inward. It begins with recognizing that even the nearest, most familiar galaxy, the one we live inside, is only partially visible, only partially understood, and deeply and irrevocably shaped by our perspective within it. The problem of counting galaxies does not begin at the edge of the observable universe. It begins here, inside a system that hides a significant fraction of itself from its own inhabitants. Once that is accepted, the humility earned, the wider problem becomes easier to frame, even if it does not become easier to solve. When we finally move our gaze just beyond the halo of the Milky Way, the first galaxies that swim into view are not subtle. They do not whisper. They announce themselves. The Andromeda Galaxy dominates the nearby cosmic landscape in scale and presence. Under a truly dark sky, free from light pollution, it stretches across a region several times the width of the full moon, a soft, elongated glow of ancient suns. It is massive, bright, and structured with sweeping spiral arms and a dense, yellowed central bulge of older stars. It feels like a cousin, a nearby peer. Slightly farther away sits the Triangulum Galaxy, smaller, fainter, but still clearly defined. Another spiral with visible lanes of dust and glowing knots of star formation. Together, these neighbours feel familiar, reassuring. They look like galaxies are supposed to look. Large, orderly, bright enough to announce themselves across millions of light years. For a long time, that familiarity shaped astronomical intuition in a quiet but powerful way. When your nearest examples all resemble one another, it is deeply tempting to assume they are typical. The Milky Way, Andromeda, and Triangulum all belong to the same broad class, grand design spirals. They contain hundreds of billions of stars, and ordered rotating disks, and extended halos of gas and dark matter. Studying them side by side creates a powerful seductive impression that galaxies, in general, are large, luminous, and easily recognizable. It is an impression that turns out to be a kind of cosmic sampling error, a bias born of proximity and brightness. Before that could become clear, however, astronomers had to answer a more basic grounding question. A question of space itself. How far away are these neighbouring systems, really? The difference between a galaxy being a few 100,000 light-years away or several million light-years away completely changes how we interpret its size, its brilliance, its nature. This is where the painstaking refinement of the cosmic distance ladder reshaped understanding. The distance ladder is not a single tool, but a collection of overlapping methods, each calibrated against the next, like a set of interlocking steps reaching out into the void. For nearby galaxies, Cepheid variable stars became the crucial rung. These pulsating stars have a miraculous property. The period of their brightness variation is tightly linked to their intrinsic luminosity. A Cepheid that pulses slowly is truly, inherently brighter than one that pulses quickly. Find a Cepheid in another galaxy, measure its pulse, and you know its true wattage. Compare that to how faint it appears, and you can calculate its distance. It's a standard candle. Astronomers like Alan Sandage devoted their careers to refining these measurements, tightening the calibrations, chasing down systematic errors, clarifying which distance indicators could be trusted at different ranges. But this work was not glamorous. It was meticulous, essential Plumbindennung, laying the secure foundation upon which the edifice of modern cosmology would be built. His work helped stabilize our understanding of how far away Andromeda and Triangulum actually are, placing them firmly outside the Milky Way and anchoring the true, humbling scale of our local universe. With distances better constrained, comparisons became meaningful. Andromeda emerged as slightly larger and more massive than the Milky Way, an older sibling. Triangulum appeared smaller, less evolved, but is still unquestionably a member of the spiral galaxy family. These differences were interesting nuances in a family portrait, but they did not immediately challenge the underlying comforting assumption that spiral galaxies represented the standard model, the default setting for galactic formation. That assumption was reinforced relentlessly by a simple fact: visibility. Large spirals are bright. Their stars are numerous. Their gas clouds glow when lit by young hot stars. Their shapes are photogenic, standing out in stark relief against the emptiness of space. When telescopes sweep the sky, these systems demand attention simply because they are easy to see. They are the low-hanging fruit of the cosmos, but visibility is not the same as abundance. This distinction is subtle, and it takes time to sink in. When the first catalogues of nearby galaxies were assembled, the most prominent objects naturally filled the pages. Spirals with clear structure dominated the early lists, not because they were the most common, but because they were the easiest to identify at a distance. They passed the most basic test: they were seen. Smaller, fainter systems blended into the background glow of the sky, often dismissed as photographic noise, plate defects, or irrelevant smudges. They were filtered out by the very process of looking. The result was a skewed, incomplete picture of the galactic population. If your attention is drawn primarily to luminous spirals, then spirals begin to feel typical. If spirals feel typical, then your estimates of how many galaxies exist begin to scale from that expectation. Bright galaxies become the reference point, the standard unit. Everything else becomes an afterthought, a minor footnote. This bias is not a failure of reasoning. It is a natural consequence of how light behaves across interstellar and intergalactic space. Bright objects announce themselves, dim objects do not. And a small galaxy containing a few million stars can be utterly overwhelmed by the glare of foreground stars within our own galaxy, or masked by a wisp of dust, or lost in the general background glow of the night sky itself. At even modest distances, our immense system may vanish entirely from view, a whisper drowned out by a cacophony. In contrast, Andromeda would remain visible, a beacon even if it were several times farther away. Its sheer size and brightness granted a kind of observational privilege, a front row seat in our surveys. That privilege, unearned, distorts our intuition. When galaxy populations are examined not anecdotally, but statistically, a different, more democratic picture emerges. Massive spirals like the Milky Way and Andromeda are impressive, majestic, but they are not numerous. They occupy only a small fraction of the total galaxy count. Most galaxies are far smaller, far dimmer, and far easier to miss. This is where Triangulum, that smaller spiral, quietly becomes more informative than it first appears. Though still a spiral, it is significantly less massive than its two larger neighbours. Its lower stellar mass, its simpler structure, it hints at a broader, hidden population of modest galaxies that do not dominate their surroundings, that do not shout. Yet, even Triangulum remains relatively bright, a respectable citizen, compared to the faintest systems we now know lurk nearby. The similarity among the nearest large galaxies once encouraged a dream of galactic uniformity. It suggested that galaxies formed in broadly similar ways, grew to comparable sizes, and followed predictable, tidy evolutionary paths. That view simplified early models and made the young, expanding universe feel more orderly, more knowable. As surveys expanded, as the sensitivity of our instruments improved by leaps and bounds, that comforting simplicity began to unravel, thread by thread. The local universe, it turned out, contained a menagerie of systems that did not resemble neat spirals at all, irregular galaxies with chaotic, splotchy shapes, as if tossed together by chance. elliptical galaxies, smooth and red, lacking disks or spiral arms entirely, resembling giant stellar beehives. And then there were the dwarfs, tiny, faint galaxies, some barely holding themselves together gravitationally. Many of these systems were found not in grand isolation, but clustered around larger galaxies like moths around a lamp, as satellite galaxies. Their existence was overshadowed, literally and figuratively, by the brilliance of their hosts. This realization forces a recalibration of intuition, a reset of expectations. The galaxies that naturally dominate our attention, that fill our textbooks, are not the ones that dominate numerically. They are statistical outliers in terms of mass and brightness. Even though they feel central to our experience, they are the cosmic exceptions. Our nearest neighbours, then, play a dual role. They provide essential, invaluable calibration points for distance, for structure, for dynamics. At the same time, they quietly mislead by over-representing a particular privileged class of galaxy. Without careful correction, they encourage an overconfidence in patterns that simply do not generalize across the vast, varied population. Recognizing this bias is not just an academic step, it is an important moment of intellectual maturation. It marks the transition when the problem of counting galaxies shifts from merely identifying the most prominent objects to the far more difficult task of accounting for the populations that do not announce themselves, that hide in plain sight. The universe does not hide most of its galaxies deliberately. It simply makes them easy to overlook. Once that is understood, attention naturally, necessarily, begins to drift away from the brightest neighbours and toward the smaller, quieter, more numerous systems that surround them. Those systems, though less impressive individually, hold the collective key to understanding how many galaxies truly exist. Galaxies rarely exist in true isolation. Although the mind's eye might picture them as lonely island universes scattered independently through the void, the reality is far more social and far more entangled. Most galaxies are born, evolve, and persist within shared gravitational environments. These environments, these neighborhoods of space, shape everything. How galaxies form their stars, how they grow, how they lose material, and ultimately how long they survive as distinct recognizable systems. To understand how many galaxies exist, then, it is not enough to simply count individual dots of light. It becomes necessary to understand the systems they belong to, the groups and clusters that form the basic scaffolding of cosmic structure. This is where our own local group becomes more than just a convenient label or a list of nearby objects. It is a living, evolving, or gravitationally bound system, a family spanning several million light-years, held together by the combined mass of its largest members, the Milky Way and Andromeda, and their immense extended halos of dark matter. Triangulum contributes its smaller but still significant mass, while dozens, perhaps hundreds of smaller galaxies orbit, drift, and interact within this same shared gravitational landscape. Their fates are woven together by gravity's invisible threads. Thinking in terms of a group immediately changes the nature of counting. Galaxies inside a group do not behave as isolated, pristine objects. Their histories overlap, their futures are intertwined. Their present appearances, whether they are ragged or smooth, star-forming or quiet, often reflect past encounters and collisions rather than some intrinsic, isolated property. From this perspective, that environment is destiny, has been explored in depth by researchers who treat galaxies not as closed, independent systems, but as participants in a dynamic, relentless tug of gravitational influence. In doing so, it reframes how a galaxy population should be interpreted. Within a group, interactions are not rare, dramatic events. They are a defining constant feature. Satellite galaxies pass repeatedly through the outer regions of their larger hosts. Tidal forces, the difference in gravity's pull from one side of a small galaxy to the other, stretch them, compress them, and sometimes tear them apart entirely. Gas, the lifeblood for new stars, can be stripped away by these encounters, or by the hot halo of the host galaxy, shutting down future star formation and condemning a small galaxy to a slow fade. Stars can be pulled out into elongated, graceful streams that wrap around the larger galaxy like cosmic ribbons, leaving visible scars of past mergers that last for billions of years. These processes directly, profoundly affect visibility. A dwarf galaxy that once contained pockets of active star formation may fade into obscurity after losing its gas, becoming a ghostly collection of old stars, harder and harder to detect against the background glow. Another may be stretched so thin by tides that it no longer resembles a coherent galaxy at all. blending instead into a diffuse cloud of stellar debris. From a purely observational standpoint, such systems are easy to miss, or to misclassify as something else entirely. This matters, and matters enormously, because the dwarf galaxies dominate galaxy populations by number. They are the silent majority. In our local group alone, more than 50 small galaxies are known, and new, ever fainter ones continue to be discovered as survey techniques improve. Many of these systems contain only a few million stars, or even just a few 100,000 compared to the hundreds of billions found in the Milky Way. Individually, they are unimpressive faint smudges. Collectively, they define the true character of the galactic population. The local group demonstrates something fundamental. The smallest meaningful unit for galaxy statistics is not the individual galaxy, but the group environment. Counting galaxies without accounting for their interactions, their births and deaths within this environment, risks a double counting of some systems and a complete missing of others. It treats a dynamic process as a static snapshot. And for example, when a dwarf galaxy is disrupted and its stars become part of a stellar stream wrapping around the Milky Way, should it still be counted as a galaxy? At what point in its dissolution does it cease to exist as a separate object? These are not merely philosophical curiosities. They directly, tangibly influence population estimates. If we only count intact, star-forming galaxies, then many systems that are clearly galaxies, but are aging or being destroyed, are excluded. If we include remnants and transitional objects, the number rises. The group context, the story of the interaction, determines which interpretation makes sense. There is also the problem of survival time. Galaxies within groups have finite lifetimes as independent systems. Over billions of years, the smaller galaxies tend to merge with larger ones or dissolve completely under unrelenting tidal forces. Our local group is not static. It is slowly, inexorably evolving toward fewer, larger galaxies through mergers and accretion. Andromeda and the Milky Way are on a collision course destined to merge in a few billion years. This means the number of galaxies present at any given moment, the number we would count in a cosmic census today, is not representative of how many galaxies have existed over time. Groups reduce galaxy counts as they age. A snapshot taken today captures only the survivors. From a statistical standpoint, this introduces a powerful bias. Older, more evolved groups will contain fewer galaxies than younger ones, even if they began with similar starting populations. Counting galaxies without considering group age and interaction history leads to deeply misleading comparisons across different cosmic environments. Isolated galaxy counts suffer from another related problem. Truly isolated galaxies are exceedingly rare. Most systems that appear isolated are simply distant from obvious neighbors or located in low-density regions. But even these galaxies are often embedded in faint filaments of dark matter and gas, part of the cosmic web, subtly influencing their evolution. By contrast, the local group offers a relatively complete nearby laboratory. Distances here are well measured. Individual stars can be resolved in many member galaxies. Tidal features can be observed directly. This makes it possible to trace interactions with a clarity impossible at greater distances. Yet even here, and in our own backyard, completeness is elusive. Some dwarf galaxies remain hidden behind the thick dust in the plane of the Milky Way. Others are so diffuse that they blend perfectly into the background of distant stars. The known population is almost certainly incomplete. We are still discovering new members of our own family. This reinforces a crucial humbling point. If the nearest and best studied galaxy group cannot be fully catalogued with absolute confidence, then more distant groups are guaranteed to be incomplete. Their faintest members slip below our detection thresholds. Their disrupted remnants are impossible to recognize as anything but noise. Counting galaxies as if they were static, independent points of light ignores these dynamic realities. It treats galaxies as fixed specimens in a catalogue when, in fact, though they are transient structures, constantly shaped by the collective dynamics. The local group shows that galaxy populations are not merely about formation. They are about survival. They depend on mass, environment, timing, and pure chance encounters. A galaxy's visibility today reflects not only what it is, but what it has endured. This is why galaxy groups are the smallest meaningful units for population statistics. They capture the context, the gravitational neighborhood, that determines which galaxies remain visible and which quietly vanish. Without that context, any count becomes an illusion of precision. a tally that mistakes a single frame of a movie for the entire story. Once this is understood, the task of counting galaxies expands again. It is no longer about tallying dots of light. It becomes an effort to account for systems in motion and shaped by shared gravity, evolving together over immense spans of time. And that makes any simple isolated galaxy count not just incomplete, but fundamentally misleading. If galaxies were counted by size or brightness alone, dwarf galaxies would barely register. They are small, faint, and often irregular in shape, lacking the grand design that makes their larger cousins so photogenic. Many contain only a few million stars, sometimes fewer, compared to the hundreds of billions found in large spirals like the Milky Way. From a distance, they fade quickly into the background, easily lost among the foreground stars of our own galaxy, or masked by dust, or drowned in instrumental noise. Yet despite their modest appearance, dwarf galaxies dominate the universe by number. In any reasonably complete survey, the dwarfs outnumber large galaxies by a wide margin, perhaps by a factor of 10, 100, or even more. They are not rare exceptions. They are the default, the most common outcome of galaxy formation. Large spirals and ellipticals draw our attention because they are dramatic and luminous, but dwarfs are the quiet majority, forming wherever small concentrations of gas manage to collapse inside their own tiny halos of dark matter. For a long time, this numerical dominance was easy to underestimate, and for a simple reason. Early galaxy catalogues were built around what telescopes could see clearly, and what they could see clearly were the bright extended systems. Dwarf galaxies slipped through the gaps, not because they were uncommon, but because they were observationally fragile. Their light was too spread out, too faint. They're too easily confused with other things. That fragility became impossible to ignore in the early 2000s when new wide-field digital surveys, equipped with sensitive CCD cameras, began to probe the sky with unprecedented depth and uniformity. As these surveys expanded, covering vast swaths of sky, something profound happened. The number of known nearby dwarf galaxies began to climb steadily, not because the universe had changed, but because the threshold for detection had finally shifted downward. Astronomers like Beth Willman played key roles in this transformation through the discovery and characterization of ultra-faint dwarf galaxies orbiting the Milky Way. These systems are among the dimmest galaxies known. They contain as few as a few thousand ancient stars spread over regions hundreds of light-years across. Then their total luminosity can be less than that of a single bright globular star cluster. Yet measurements of the motions of their stars reveal something extraordinary. They are embedded in dark matter halos, massive enough to qualify them as genuine galaxies. Their gravity is dominated by the unseen. The existence of these ultra-faint dwarfs exposed a crucial limitation in all early accounts. Galaxies had been missing not because they were hidden at great distances, but because they were barely luminous at all. Once survey sensitivity improved, these ghostly systems began to appear in significant numbers, often clustered around larger galaxies like faint attendants. This discovery highlighted an uncomfortable, inescapable truth. The number of galaxies one finds depends overwhelmingly on how faint one is able to look. The lower the detection threshold and the count rises. Raise it and the universe appears simpler, emptier, and more manageable than it really is. Dwarf galaxies are not just faint, they are also vulnerable. Their low masses make them susceptible to tidal stripping when they orbit larger galaxies. As they pass through the powerful gravitational field of a massive host, stars can be pulled away, gas can be removed, and the remaining system can be stretched into elongated, dissolving shapes. Over time, some dwarfs lose so much material that they are reduced to mere stellar streams, no longer recognizable as self-contained galaxies. This introduces the critical idea of a survival threshold. Below a certain mass, a galaxy likely cannot retain its stars and gas against external forces. It may form, but it will not persist for long as a coherent entity. Above that threshold, it can survive repeated interactions and remain visible for billions of years. The exact value of this threshold isn't fixed. It depends profoundly on environment. A dwarf galaxy in isolation, far from any giant neighbour, may survive with far less mass than one orbiting close to a spiral like the Milky Way. This means the same type of galaxy can have a very different lifetime, a different fate, depending entirely on where it lives. From a counting perspective, this matters enormously. Some dwarf galaxies exist only briefly as identifiable systems, others persist quietly for cosmic timescales. A snapshot taken at any given moment captures only those that have survived up to that point. It is a census of survivors, not of all that were born. There's also the persistent nagging problem of classification. Many dwarf galaxies blur the line between galaxies and star clusters. Both can contain similar numbers of stars, both can appear compact or diffuse. The key difference lies in gravitational binding and dark matter content, neither of which is directly visible. In practice, astronomers must rely on indirect clues, primarily stellar motions. If the stars are moving too fast to be held together by the gravitational pull of the visible stars alone, then the presence of a significant dark matter halo is inferred, and the object is classified as a galaxy. If the observed motions can be explained by the visible mass, it is usually labelled a star cluster. This sounds straightforward in theory, but in reality it is messy. Measurements of motions in these faint systems are uncertain, sample sizes are small, boundaries are fuzzy. As a result, some objects sit uncomfortably between categories, included in some galaxy counts and excluded from others. Each of these judgment calls nudges the total number up or down. Dwarf galaxies also challenge our intuitive ideas about shape and structure. Many lack clear disks or bulges. Some appear irregular, with star formation occurring in scattered, seemingly random regions rather than organized spiral patterns. Others are spheroidal, containing only old red stars and little gas, their active phases of star formation long over. These differences are not merely cosmetic, they reflect distinct evolutionary paths shaped by environment, initial mass, and timing. When counting galaxies, treating all dwarfs as a single, a monolithic category can obscure this rich diversity, while splitting them too finely can inflate uncertainty. What remains consistent, however, is their sheer abundance. In galaxy groups like the local group, dwarfs outnumber large galaxies by at least an order of magnitude. In richer, denser environments such as giant galaxy clusters, the imbalance is even more extreme, with thousands of dwarfs swarming around a few hundred giants. This has a direct and unavoidable consequence for estimates of how many galaxies exist in the universe. If most galaxies are small and faint, then most galaxies are, by their very nature, difficult to detect. Any survey that misses faint objects will systematically, unavoidably undercount the total population. As detection limits improve, counts rise. And as classification criteria broaden to include more marginal objects, counts rise again. This is not a sign of error or indecision in the field. It is a true reflection of the underlying population. The universe does not consist of a modest number of grand, luminous structures surrounded by empty space. It consists of vast numbers of modest systems, many hovering perpetually near the edge of detectability, many shaped or damaged by their surroundings, many short-lived on cosmic timescales. Dwarf galaxies are the statistical backbone of galaxy counts. They set the scale, they dominate the numbers, and they quietly ensure that any attempt to count galaxies must remain provisional, opened to revision. When astronomers revise their estimates upward, as they have done repeatedly over the decades, dwarfs are almost always the reason. And not because new revolutionary physics has been discovered, but because the universe simply turns out to be more crowded, more packed with small, faint structures than our initial intuition, shaped by the brightest examples ever suggested. Understanding this shifts the question of how many galaxies exist, away from dramatic extremes and towards subtle limits. It becomes less about how far our telescopes can see, and more about how faint a system can be and still be recognized as a galaxy at all. That recognition, fragile and conditional, is what keeps the total number rising, a slow tide of discovery against the shore of our ignorance. At first glance, the word galaxy feels unambiguous. It sounds like a clearly defined thing. A large system of stars held together by gravity, distinct from its surroundings, are recognizable when you see it. In practice, however, that clarity dissolves very quickly under scrutiny. Astronomers do not count galaxies the way one might count planets or moons. Before anything can be counted, it must be defined. And that definition, it turns out, is far more slippery, more contingent, than intuition suggests. One way to define a galaxy is through its dynamics. A galaxy must be a gravitationally bound system, meaning its stars move in ways that indicate they are trapped in a shared gravitational well, not just passing near each other. This criterion immediately excludes loose, unbound associations of stars. It also elevates the importance of measuring stellar motions because motion reveals mass, including the mass that cannot be seen, the dark matter. Another approach focuses on stellar populations, and a galaxy typically contains multiple generations of stars, often spanning billions of years in age. This suggests a long-lived system capable of forming stars repeatedly over cosmic time, recycling its gas. By contrast, many star clusters form their stars in a single, brief burst and then fade. That difference sounds straightforward, but in small, faint systems, the distinction can blur alarmingly. Dark matter. Content adds yet another layer. Modern definitions often require a galaxy to be embedded in a dark matter halo. This criterion is especially important for dwarf galaxies, where the visible stars may account for only a tiny fraction of the total mass. If the stars are moving too quickly to be explained by their own gravity alone, dark matter is inferred, and the system is pushed into the galaxy category. Each of these definitions captures something real, something important, but none is complete on its own. Some systems satisfy all criteria with flying colours, others satisfy only one or two. The question then becomes, which properties matter most? Where do we draw the line? These ambiguities were explored in depth by astronomers who spent their careers analysing galaxy morphology and classification. Their work highlighted how easily galaxies resist tidy categorization. Even among large, spectacular systems, shapes vary smoothly across a spectrum rather than falling into neat, discrete boxes. Among smaller, fainter systems, the boundaries become even more porous, more a matter of consensus than cold fact. Classification schemes, as this work showed, are not neutral description. They encode deep assumptions about formation, evolution, and what we consider important. When those assumptions change, when we understand that dark matter is fundamental or that star formation history is key, the categories change with them. This has a quiet but powerful effect on galaxy counts. When astronomers publish estimates of how many galaxies exist, those numbers often differ, not because the observations themselves disagree, but because the definitions underpinning the count do. One study may include ultra-faint dwarfs as galaxies. Another, looking at the same data, may exclude them, classifying them as extended star clusters. A third may reclassify the same object based on new, more precise data about stellar motions. Each choice is defensible. Each choice alters the final count. These shifts rarely make headlines. They occur in the footnotes of papers, in the columns of data tables, in the dry language of methodological sections. Yet collectively they move the number of known or inferred galaxies up or down by significant margins. The problem becomes even clearer when considering how galaxies support themselves against gravity's relentless pull. Some galaxies are rotation-supported. Their stars orbit a central axis in an organized disk, like the Milky Way or Andromeda. Rotation provides stability, and the system's structure is relatively easy to interpret. Others are pressure-supported. In these systems, stars move in random, chaotic directions, held together not by coherent rotation, but by the collective, statistical effect of these random motions, like bees in a swarm. Elliptical galaxies and many dwarf spheroidals fall into this category. Their shapes are smoother, their dynamics less intuitively graspable, and their boundaries, where the galaxy truly ends, are harder, sometimes impossible, to define. Pressure-supported systems challenge our simplest ideas of what a galaxy looks like. They may lack clear edges. Their stars fade gradually, imperceptibly, into the surrounding space of the group or cluster. In some cases, it is genuinely unclear where the galaxy ends and the background or intracluster light begins. This matters immensely for counting. A rotation-supported disk presents a relatively clear bounded signal. A pressure-supported cloud of stars does not. Detection becomes sensitive to a subjective decision. How far out do we draw the boundary? Which stars are included as part of the galaxy, and which are dismissed as foreground or background contamination? The issue grows sharper, more problematic at the smallest scales. Some ultra-faint systems contain only a few thousand stars. Their internal motions, measured with great difficulty, might suggest the presence of dark matter, but the measurements are noisy, uncertain. Their stellar populations might closely resemble those of ancient star clusters. Their shapes are irregular, amorphous. Classifying them requires scientific judgment as much as raw measurement. It is not uncommon for different research groups to reach different conclusions about the same faint smudge of light. One catalogue lists it as a galaxy, another lists it as a cluster. Neither conclusion is obviously wrong. They are simply applying different thresholds, weighting different pieces of evidence slightly differently. This is why taxonomy itself becomes a limiting factor in galaxy counting. The universe does not present galaxies as neatly labelled entities. It presents a continuum of structures, a smooth distribution ranging from massive luminous spirals to barely bound stellar assemblages hovering on the very edge of coherence. Counting requires drawing lines across that continuum. Those lines are not arbitrary, they are guided by physics and observation, but they are not uniquely determined by nature either. They reflect the current state of theory, the available data, and the specific questions being asked. A study focused on dark matter distribution may adopt one definition, emphasizing gravitational binding. A study focused on star formation history may adopt another, emphasizing stellar populations. As a result, the number of galaxies is not a single objective fact waiting passively to be discovered, and it is a quantity that emerges from a set of choices, each grounded in physical reasoning, but none immune to revision as our understanding deepens. This does not mean galaxy counts are meaningless. Far from it. It means they are conditional. They describe how many galaxies exist according to specific criteria within specific observational limits at a particular moment in scientific understanding. There's a quiet irony here. As telescopes improve and data becomes richer, the problem does not simplify. It becomes more detailed, more nuanced. More objects appear near the boundary, in the grey area. More exceptions demand explanation. More systems resist clean classification. In a sense, the universe becomes both more crowded and less tidy at the same time. This is why published galaxy counts, when they are responsible, they tend to be ranges rather than precise totals. They acknowledge that definitions matter. They admit that some objects sit uncomfortably between categories. They reflect intellectual humility rather than mere uncertainty. When astronomers say there may be hundreds of billions, or even trillions of galaxies, that statement carries an implicit, unspoken clause. It depends. It depends on what is counted, how faint is too faint, and where the line between galaxy and non-galaxy is drawn. Understanding this subtly reframes the question itself. Asking how many galaxies exist is not just a question about abundance, it is a question about identity. It asks what kind of structures we consider meaningful, persistent, and worthy of the name. The answer evolves because the universe is more inventive, more varied than our classification schemes. And every time those schemes are refined, the count shifts quietly in response, not as an admission of error, but as a sign of growing, deepening knowledge. There was a time when galaxies did not exist as a category at all. The night sky contained stars, planets, and a scattered collection of faint, misty objects known collectively as nebulae. Some of these, like the Orion Nebula, were clearly associated with star formation, glowing clouds inside our own Milky Way. Others were unresolved smudges, their nature utterly unclear. Through the telescopes of the 18th and 19th centuries, they all looked broadly similar, soft-edged, with no obvious stars and no reliable sense of distance. Without distance, size is meaningless. Without size, classification collapses. Astronomers could describe where these nebulae appeared, how bright they seemed, and sometimes how their light was distributed, but they could not say what they actually were. A faint spiral shape in the eyepiece might indicate a nearby cloud of gas lit by newborn stars, or an unimaginably distant island of stars, a universe in itself. Both interpretations fit the meagre data equally well. This ambiguity was not a failure of imagination. It was a stark limitation of tools. Telescopes of the time gathered relatively little light. Long exposures were difficult. Photographic plates were still new and crude. Even the largest instruments struggled to resolve individual stars in anything beyond the immediate surroundings of the Milky Way. As a result, most nebulae remained unresolved, their true nature hidden behind the same haze that made them intriguing. The problem was compounded by the sheer scale of the question, and if spiral nebulae were part of the Milky Way, then our galaxy itself would have to be enormous, extending far beyond any reasonable distribution of visible stars. If they were external systems, then the universe would suddenly become vastly, terrifyingly larger than anyone had imagined. Both possibilities were unsettling, and neither could be tested decisively with the instruments at hand. Into this profound uncertainty stepped a different kind of observation. Rather than asking how nebulae looked, astronomers like Vesto Slipher began asking how they moved. At the Lowell Observatory in the early 1900s, he turned a spectrograph towards spiral nebulae and measured their spectral lines with extraordinary care and patience. What he found was unexpected and would later become a cornerstone of modern cosmology. And many of these nebulae exhibited large Doppler shifts. Their spectral lines, the chemical fingerprints of hydrogen, oxygen, calcium, were displaced toward the red end of the spectrum in ways that indicated recessional motions of hundreds of kilometers per second, far faster than the typical motions of stars within the Milky Way. A few appeared to be approaching, but the vast majority were racing away. At the time, there was no accepted framework to interpret this. Cosmic expansion had not yet been proposed by Friedman or Lemaitre. The idea that the fabric of space itself might be stretching was not part of mainstream astronomy. Slipher's measurements stood alone, precise but deeply puzzling. If spiral nebulae were small, local objects within the Milky Way, such extreme systematic velocities would be extraordinarily difficult to explain. The stars orbiting the galactic center move at a few hundred kilometers per second at most, and those motions follow predictable, gravitationally bound patterns. These nebulae did not fit comfortably into that picture. Slipher did not claim to have discovered external galaxies. What he provided was something more subtle, and in the long run more important. He provided evidence that these objects were dynamically distinct from the stars around them. They behaved as though they were separate systems, not local clouds. Even so, interpretation lagged behind observation. Many astronomers clinging to the known scale of the Milky Way continued to classify spiral nebulae as internal features. Others, sensing a revolution, argued they were external island universes. The debate persisted not because one side ignored the data, but because the data was still incomplete. Velocities alone could not establish distance. Without distance, true size and nature remained ambiguous, a matter of faith as much as fact. This misclassification had a profound consequence for counting. If spiral nebulae were assumed to be internal, then they were not counted as separate galaxies. They were treated as interesting but minor substructures within a single, grand system, the Milky Way. Population studies, the very idea of counting galaxies, stalled because, by definition, there was only one galaxy to study. This conceptual bottleneck delayed the emergence of galaxy statistics by decades. It was a period of cosmic myopia where the universe felt both known and strangely constrained. Instrumental limits played the decisive role. Early photographic plates were insensitive to faint light, particularly the red light of older stars. Even if a spiral nebula contained billions of stars, those stars would blur together into a smooth, unresolved glow unless they could be picked apart into individual points of light. Only the nearest systems could be resolved, and even then only under ideal conditions. Dust further complicated matters. Dark lanes within the Milky Way obscured large portions of the sky, particularly along the galactic plane where many nebulae were observed. A distant galaxy viewed through a thick screen of our own galaxy's dust could appear small and faint, easily mistaken for a local, insignificant puff of gas. The universe was not only vast, it was cluttered with obstructions, veils drawn across our view. As telescopes improved incrementally, but the picture shifted slowly rather than dramatically. Larger mirrors collected more light, better optics improved resolution, longer exposures revealed hints of structure within some nebulae. Spiral arms became clearer. Bright knots appeared that were suggestive of star-forming regions. Yet even these improvements did not settle the great question. Structure alone could not distinguish between a nearby cloud and a distant galaxy. Nature, inconveniently, can produce similar patterns, spirals, glows, clusters, at vastly different scales. The turning point required a new kind of measurement, something that tied observable behavior to intrinsic properties, something that could break the distance deadlock once and for all. That solution would come from variable stars whose predictable pulsations would act as a standard candle, allowing astronomers to measure distances far beyond the reach of simple geometry. But before that breakthrough arrived, the universe existed in a kind of conceptual limbo. Galaxies were there, but unnamed. Countless stellar systems existed beyond the Milky Way, but they were hidden inside a category, nebula, that blurred the near and the far together. The universe was already crowded, but to us, it looked sparse, containing little beyond our own stellar home. This period of profound ambiguity shaped how astronomers thought about the cosmos. It encouraged a disciplined caution. It reinforced the idea that classification must wait for measurement, that naming is not knowing. It also left a legacy of humility that still resonates in astronomy today. The lesson is straightforward, but easy to forget in an age of instant data. Observations do not speak for themselves. They are filtered through instruments, through assumptions, and through the available intellectual frameworks of the time. When tools are limited, interpretation narrows accordingly. The recognition of galaxies as separate worlds did not happen because the universe changed. It happened because the means to distinguish distance, motion, and structure finally converged. Once that convergence occurred, the population of the universe expanded almost overnight, not in reality, but in human understanding. Before that moment, galaxies were not rare. They were simply invisible as galaxies. And that historical invisibility reminds us always that any count of cosmic structures is inseparable from the tools we use to reveal them. So for years, the argument over spiral nebulae was not about imagination or belief, it was about method. The disagreement that crystallized in the so-called Great Debate of 1920 was, at its core, a clash between different ways of reasoning from incomplete data. One side, represented by Harlow Shapley, argued from the distribution of stars and globular clusters within the Milky Way, concluding that our galaxy was vast enough to contain all known nebulae. The other side, led by Heber Curtis, focused on the high velocities and occasional novae seen in spiral nebulae, suggesting they were separate systems far beyond the Milky Way's boundaries. Both positions were grounded in evidence. Both relied on assumptions that seemed reasonable at the time. What neither side possessed was a reliable, a universally accepted way to measure distances on truly extragalactic scales. Without distance, everything else remained tantalizingly uncertain. A spiral nebula could be a small nearby celestial ornament or an enormous distant continent of stars. Its brightness alone could not resolve the ambiguity. Its structure did not help either, since nature has a habit of repeating patterns at different scales. The debate persisted not because the data were ignored, but because they were insufficient to force a conclusion. The community was waiting for a key. The breakthrough came from a source that initially had nothing to do with galaxies at all. Henrietta Swan Leavitt was studying variable stars in the Small Magellanic Cloud, a faint, blurry companion to the Milky Way. While analysing stacks of photographic plates, and she noticed a simple but profound relationship among certain variable stars, later called Ephites. These stars pulsed rhythmically, and Leavitt discovered that the period of their pulsation was tightly linked to their intrinsic luminosity. A Cephid with a long pulse period was inherently, physically brighter than one with a short period. This relationship, once calibrated, transformed Cepheid variables into the first reliable cosmic distance markers for beyond our galactic neighbourhood. By measuring how long a Cepheid took to brighten and fade, its true brightness could be inferred. Comparing that intrinsic brightness to its apparent observed faintness allowed its distance to be calculated with newfound confidence. Crucially, this method did not depend on the star's location within the Milky Way, and it could be applied anywhere Cephides could be observed. Once this period luminosity relationship was calibrated using nearby Cepheids with distances measured by other means, it became a critical rung on the distance ladder, one that extended far beyond previous limits. Distances that were once speculative could now be measured. When Cepheid variables were finally identified inside spiral nebulae, most famously by Edwin Hubble in the Andromeda Nebula in 1923, the implications were immediate and earth-shattering. The distances derived were far, far too large for these objects to reside within the Milky Way. They were millions of light-years away, placing them firmly outside any plausible boundary of our galaxy. This was not a gradual shift in understanding. It was a step change, a fracture in cosmic perspective. Overnight, the universe expanded from a single galaxy to a population of many. Objects that had been treated as internal features, as celestial curiosities, suddenly became independent stellar systems, each comparable in scale to the Milky Way itself. The shock was not just quantitative, it was deeply conceptual. The Milky Way was no longer the universe. It was one example among many, a large example, certainly, but no longer central by definition. The night sky, once interpreted as a sparse arrangement of stars with a few local clouds, was recast as a window into a universe densely, richly populated with galaxies. Every faint smudge became a potential universe of its own. This reframing immediately, irrevocably altered the problem of counting. Before this recognition, the number of galaxies was effectively 1. Afterward, and it was suddenly unbounded, exploding into possibility. Every spiral nebula became a candidate galaxy. Every faint patch of light raised new thrilling questions. The universe did not merely contain more structure. It contained orders of magnitude more structure than anyone had dared to presume. Importantly, this moment did not deliver closure. It delivered a thrilling, disorienting vertigo. Astronomers now faced a universe far larger than expected, populated by objects that could not yet be counted systematically. Telescopes could identify some of the brighter nearby galaxies, but the vast majority remained beyond reach, their numbers a matter of guesswork. The question shifted from what galaxies were to how many there might be. This transition marked the true birth of galaxy demographics. Once galaxies were recognized as separate worlds, it became possible, necessary even, to ask statistical questions. How many galaxies exist nearby? How are they distributed in space? Is the Milky Way typical or unusual? These questions could not have been meaningfully posed before the distance scale was established. They depended on galaxies being comparable objects, members of a class rather than ambiguous singularities. The Great Debate is sometimes remembered as a contest with a clear winner and loser. That framing misses the deeper point. The debate was resolved not by rhetoric or superior argument, but by measurement. Neither position collapsed under criticism. It was overtaken by new data. The resolution also revealed a recurring essential pattern in astronomy. Progress often arrives not as a gentle refinement of existing ideas, but as a dramatic redefinition of what is even being discussed. Once galaxies were recognized as independent systems, the entire vocabulary of the field changed. The Milky Way became one galaxy among many. Nebulae became galaxies. The universe became structured on scales that demanded new theories, new tools, and a new humility. There is a subtle consequence of this shift that matters deeply for counting. Early galaxy counts, born in the wake of this revelation, were built on a sense of astonishment. Each new galaxy discovered felt like a revelation, a new world mapped. Catalogues grew rapidly as telescopes improved, but there was no clear sense of completeness. The sky seemed to offer an endless supply of new systems, receding into the darkness. This sense of abundance was real, but it was also uneven, bright. The nearby galaxies were catalogued first, faint distant ones lagged behind. The distribution of known galaxies reflected observational reach, what was easy to see, rather than the true underlying population. Still, the recognition of galaxies as separate worlds changed the baseline permanently. Counting galaxies was no longer about expanding the boundaries of a single system. It was about mapping a population, taking a census of the cosmos. The scale shock lingered, even as astronomers became accustomed to thinking in terms of millions of light years. The full implications continued to unfold like an endless ripple. If nearby space contained dozens of galaxies, how many lay just beyond? If telescopes revealed more with each improvement, was there any limit at all? These questions did not arise from mere speculation. They emerged directly, or forcefully, from measurement. The universe had revealed itself to be far larger than expected, and that revelation carried with it a burden of wonderful, terrifying uncertainty. The beginning of galaxy demographics did not provide numbers. It provided a framework, a way of thinking about galaxies as a population rather than a curiosity, a recognition that abundance, not isolation, defined the cosmos. From that point on, every improvement in observation added to the count. Not because galaxies were appearing out of nowhere, but because the means to recognize them was steadily improving. The discovery that galaxies are separate worlds did not answer how many exist. It made the question unavoidable, central, and infinitely compelling. And that challenge has been unfolding ever since, shaped by tools, definitions, and the quiet reminder that the universe is rarely as simple as our first impressions suggest. Once galaxies were recognized as separate systems, the next impulse was straightforward human: count them. If the universe contained many galaxies rather than one, then it should be possible, at least in principle, to catalogue them, tally them, and arrive at a meaningful total. Early astronomers approached this task with the tools they had, and for the first time those tools included the ability to record the sky systematically, permanently. Photographic plates transformed astronomy in the late 19th and early 20th centuries. Unlike the human eye, a photographic plate could accumulate light over hours, even days, gathering faint signals that would otherwise be invisible. Exposures lasting through long, cold nights revealed countless dim objects scattered across the sky, many of them the spiral nebulae now understood to be galaxies. These plates made repetition and comparison possible. The same region of sky could be recorded, surveyed, measured and catalogued. Patterns began to emerge from the fog of dots. Certain regions appeared richer in galaxies than others. Some galaxies seemed to cluster together, while others sat in lonely isolation. Early catalogues were assembled from these images, listing positions, apparent brightness, and rough morphological shapes. For the first time, the universe began to look like something that could be inventoried, that had a quantifiable population. But this new appearance of order concealed deep systematic limitations. Photographic plates had finite sensitivity and a strong bias. They responded well to blue light, the light of hot young stars, but poorly to red light, the glow of older stellar populations. This meant faint galaxies dominated by the red stars were underrepresented, often missing entirely. Dust absorption, both in our galaxy and in the distant galaxies themselves, further reduced visibility, particularly near the plane of the Milky Way. Even in the clearest, darkest regions of sky, the plates captured only a fraction of what was truly there. Brightness became the primary unyielding filter, whether astronomers intended it or not. Only galaxies above a certain apparent brightness threshold made it into the catalogues. Everything fainter effectively did not exist as far as the data were concerned. This is where the concept of the luminosity function enters the story, a cornerstone of statistical astronomy. The luminosity function describes not individual galaxies, but the statistical distribution of a population, how many galaxies exist at different intrinsic brightness levels. Early work on this concept recognized a fundamental truth. Bright galaxies are rare, and faint galaxies are common. The great challenge, then and now, lay in measuring the faint end of that distribution. To know the true number, you have to see the faintest members. Fritz Zwicky played a pivotal role in shaping this statistical, population-based way of thinking. While studying the Coma cluster of galaxies in the 1930s, he noticed something peculiar and profound. The motions of galaxies within the cluster were far too fast to be explained by the gravitational pull of the visible mass alone. And this led him to propose the existence of large amounts of unseen matter, Dunkel materia, what we now call dark matter. Although his ideas were controversial and largely ignored for decades, his approach had broader implications. Zwicky treated galaxies as members of populations, as test particles in a gravitational field. He considered how many galaxies of different types existed within clusters and how mass was distributed among them. This statistical mindset, this focus on collective properties over individual wonders, was essential for counting on cosmic scales. However, early attempts to apply it ran headlong into observational bias. Faint galaxies were not merely undercounted, they were often entirely absent from the data. When astronomers plotted the number of galaxies as a function of brightness using these early catalogues, the curve appeared to drop off sharply at low luminosities. It looked as though the universe contained relatively few faint galaxies. That conclusion was comforting. It suggested a knowable, limited population, but it was wrong. The apparent scarcity of faint galaxies was not a feature of the universe, it was a feature of the instruments. Below a certain brightness, galaxies simply vanished from the photographic plates, swallowed by the noise of the emulsion and the sky glow. The luminosity function was being truncated by technology, not by nature. This created a systematic bias that was difficult to recognize at first. Because the same bias affected most surveys of the era, their results appeared consistent. Different catalogues agreed with one another, reinforcing a false confidence in their completeness. The missing galaxies were missing everywhere, so their absence wasn't noticed. Bias also crept in through subtle selection choices. Early surveys often focused on visually interesting regions or areas known to contain rich clusters. Seemingly empty regions of sky received less attention. This skewed perceptions of how galaxies were distributed across space, making the universe appear clumpier than it is, and emptier in the voids. Classification introduced further distortion. Galaxies with clear spiral structure were easy to identify and catalogue. Elliptical galaxies, with their smooth, featureless light profiles, were sometimes mistaken for faint stars, especially at great distances. Small, diffuse galaxies were often written off as plate defects, scratches, or background noise. Even when a faint galaxy was detected, and its distance was hard to estimate without resolved stars or clear features. Without a reliable distance, it was difficult to determine whether the object was a small galaxy nearby or a giant galaxy far away. Many were excluded from counts simply because they could not be placed confidently in the three-dimensional map. All of these factors — sensitivity, selection, classification, distance, uncertainty — pushed early galaxy counts decisively downward. The universe appeared simpler, sparser, and less crowded than it really was. Estimates of the total number of galaxies rose only slowly as surveys expanded, but they remained anchored to the bright, easily detected systems. The true teeming abundance of faint galaxies remained hidden, a secret the universe was not yet ready to give up. There was also an implicit, unchallenged assumption at work. Early astronomers often assumed that the galaxies they could see were representative of those they could not. This assumption seemed reasonable, even necessary. It allowed small, bright samples to be extrapolated to vast, dark volumes. But it relied on the idea that galaxy populations did not change dramatically with brightness or mass, that small galaxies were just scaled-down versions of large ones. As later observations would starkly reveal, that assumption does not hold. The majority of galaxies are small and faint, but they are not simply miniature spirals. They are a different population altogether, with different formation histories, different shapes, and different fates. Their contribution to the total number of galaxies is overwhelming, and even though their contribution to the total light of the universe is modest, early surveys, constrained by technology, effectively counted light. They captured the light budget of the cosmos reasonably well, but they missed most of the population count. This distinction between light and number is subtle but crucial, a recurring theme in our story. A small number of large, brilliant galaxies can dominate the light in a patch of sky, while a vast number of small, faint galaxies dominate the tally of objects. Counting light is easier than counting objects. Early astronomy, bound by the limits of photographic plates, effectively counted light. The methods themselves embedded this bias. Detection thresholds were fixed by emulsion grain. Classification schemes favoured well-resolved photogenic shapes. The survey areas were chosen for convenience or visual interest rather than statistical completeness. Each choice seemed practical, sensible at the time. Together, they painted a coherent but incomplete picture of the universe. These early efforts were not failures. They were necessary, heroic first steps. They established the monumental fact that galaxies existed in large numbers and that they were not distributed randomly, but followed a cosmic web. They introduced the statistical tools, the luminosity function, the idea of selection bias, that would later be refined and corrected. Most importantly, they revealed that counting galaxies was not, and never could be, a simple act of observation. It was, from the very beginning, an inference problem. As technology improved, astronomers began to revisit these early catalogues, and comparing them with deeper, clearer observations. Discrepancies emerged, gaps were revealed. Regions once thought to be sparse were found to contain dozens of faint galaxies. Famous clusters appeared richer, more populated, when observed with more sensitive instruments. Corrections were applied. Luminosity functions were extended gingerly toward lower brightness. Biases were slowly quantified and modelled. Each correction pushed galaxy counts upward, not as an error, but as a refinement. The early attempts to count the universe did not produce a final number. They produced a lesson, etched deep into the methodology of cosmology. The number of galaxies one finds depends irrevocably on how one looks, on what one is able to detect, and on which assumptions are built, often invisibly, into the method. And that lesson would guide every later effort as astronomers move from photographic plates to digital detectors, from hand-drawn catalogues to automated surveys, and from counting what is obvious to accounting for what is almost invisible. The universe had already been crowded. We were only beginning haltingly to learn how to count it. Distance in the universe is never just distance. It is also a journey back in time. Every time a photon travels across space, it also travels across epochs. This means that looking farther away is fundamentally the same as looking further into the past. Nearby galaxies are seen as they exist now, or nearly now, shaped by billions of years of evolution. Distant galaxies are seen as they were long ago, often when the universe itself was in its youth, a different place entirely. This effect, known as look-back time, changes the meaning of observation in a way that is both simple and profoundly complex. When astronomers observe a galaxy 10 million light-years away, they see it as it was 10 million years ago, a blink in cosmic terms. At 1 billion light-years, the image captures a state from 1 billion years in the past, a significant chapter back. At redshifts of 1, 2 or more, galaxies are seen during their earlier, often violent stages of formation. As a result, the universe does not present us with a single uniform population of galaxies at different distances. It presents a layered history, a cosmic archaeological dig. Nearby galaxies tend to be mature, settled systems. Many have finished their major growth spurts. Their spiral arms are well defined. Their star formation has settled into a gentle simmer, or stopped altogether in the case of elliptical galaxies. These galaxies reflect the outcome of long evolutionary processes. Mergers, interactions, gradual gas depletion, the quieting of youth. Distant galaxies tell a different story. They are often smaller, more compact, more irregular. Star formation rates tend to be ferociously high. Structures are less settled, more chaotic. Some appear clumpy or distorted, not because they are abnormal, but because they are young, still assembling, still reeling from collisions and rapid inflows of gas. This intrinsic evolutionary difference matters deeply for counting galaxies. If distant galaxies were simply farther away versions of nearby ones, counting would be a relatively straightforward exercise in geometry and brightness correction. One could simply account for distance and dimming, then extrapolate. But because galaxies evolve, the distant population is not a mirror of the nearby population. It represents earlier, often wildly different, stages in the life cycle of galaxies. This complicates any attempt to estimate how many galaxies exist at a given time, especially now. The challenge is compounded by the concept of an observational horizon. In relativistic cosmology, this horizon defines the maximum region of the universe from which light has had time to reach an observer since the beginning of cosmic expansion. Beyond that boundary, light has not yet arrived. No matter how powerful a telescope, we cannot see beyond this horizon. It is not a physical wall, but a limit imposed by time and the finite, unbreakable speed of light. The observable universe is not the entire universe. It is the portion that has had time to reveal itself to us. This distinction is essential, non-negotiable for galaxy counting. Any empirical count is automatically forever restricted to the observable universe. Galaxies beyond the horizon may exist in enormous numbers, but they cannot be observed directly or indirectly. They must be excluded from any count based on evidence. Even within the observable universe, distance introduces additional punishing limits. As galaxies recede farther into the past, their light becomes not only fainter but stretched and diluted. One of the most important consequences is surface brightness dimming. Surface brightness refers to how much light is received per unit area on the sky, the concentration of the light. As distance increases, though the total light from a galaxy spreads over a larger area in our telescope's image. Furthermore, the expansion of the universe itself saps the energy of each photon. The combined effect causes a galaxy's surface brightness to decrease rapidly with distance. This means that even if a distant galaxy has the same intrinsic total brightness as a nearby one, it will appear much, much fainter per square arcsecond of sky. Extended, diffuse galaxies suffer most from this effect. Their light becomes so spread out that it falls below the detection threshold of even our deepest surveys, even when their total luminosity might be quite substantial. Compact galaxies, or dense regions within galaxies, fare better. A brilliant knot of star formation can remain visible at great distances, while the extended disk around it fades into invisibility. This introduces a powerful distorting selection effect that favours certain types of galaxies over others as we look back in time. As distance increases, the universe, in other words, becomes biased towards showing us only its brightest, densest, most compact structures. The quiet, diffuse majority fades from view. This bias fundamentally affects how we interpret galaxy populations. Surveys of the distant universe tend to detect small, compact, intensely star-forming systems. Large, diffuse, slowly rotating disks may have existed at those early epochs, but their light is too spread out to be detected reliably. As a result, the distant universe appears populated by galaxies that look very different from nearby ones. Some of that difference reflects genuine, dramatic evolution. Some of it, however, reflects the cruel limits of observation and a filter imposed by physics. Separating these two effects, true evolution from observational bias, is one of the hardest tasks in extragalactic astronomy. Errors in that separation directly, significantly affect galaxy counts. There is another subtlety, another layer. The galaxies we see at great distances are not necessarily the direct linear ancestors of the galaxies we see nearby today. The family tree is not a simple chain. Many early galaxies merge with others, forming larger systems. Some are destroyed entirely, their stars scattered. The number of galaxies decreases over time through mergers, even as the total stellar mass in the universe increases. This means that counting galaxies at different distances is not counting the same population at different ages. It is counting different successive snapshots of a changing, a mixing system. At earlier epochs, the universe contained more galaxies, but they were on average smaller and less massive. Over time, mergers reduced their number while increasing the size of the survivors. The nearby universe contains fewer galaxies, but on average they are larger. This creates a profound tension in interpretation. Should galaxy counts focus on how many galaxies exist now, or how many have ever existed? These are different questions with wildly different answers. Most observational studies, and the headline numbers we hear, aim for the present-day count within the observable universe. But those counts are informed by data drawn from across cosmic time, requiring careful, model-dependent translation to connect past populations to present estimates. Light itself becomes a filter in another way. And as we look to higher redshifts, the light from young stars originally emitted in ultraviolet is stretched into optical and then infrared wavelengths. Before space-based infrared telescopes like Spitzer and Webb were available, entire populations of early galaxies were invisible to us. They were not absent. They were simply shifted out of our view, their light waiting in a part of the spectrum our eyes and early instruments could not seize. This reinforces the recurring humbling theme. The number of galaxies we can count depends on the properties of light, the age of the universe, the expansion of space, and the sensitivity of our instruments across a broad spectrum. It is not a static quantity waiting passively to be discovered. Look-back time ensures that distance always comes with evolution, and observational horizons ensure that some regions remain permanently inaccessible. Surface brightness dimming ensures that many galaxies fade away before we can recognize them. Together, these effects mean that the distant universe is not just farther away. It is fundamentally, intrinsically harder to see and to interpret. This difficulty does not make galaxy counting impossible, but it demands immense care, explicit caveats, and a willingness to live with uncertainty. Astronomers must build models of how galaxy populations change over time, of how observational biases distort our samples, of how many faint systems we are missing at each redshift. Each correction adds a layer of uncertainty. Each assumption carries consequences. Yet despite these formidable challenges, patterns do emerge, and they are robust. Galaxy populations grow denser as we look toward the past. Small galaxies become more common relative to large ones. Star formation rates rise the farther back we look, structures appear simpler, more chaotic. These patterns provide clues, a narrative. They allow astronomers to estimate with ever-improving confidence how many galaxies existed at different times and how many remain today within our observable volume. Still, the limits remain, hard and fast. No telescope can see beyond the observational horizon. No observation can escape the influence of look-back time. No image is free from the effects of dimming and selection. Counting galaxies, therefore, is not merely a spatial problem, a matter of scanning volume. It is a temporal one. It requires accounting for a universe that changes as it is observed, and a universe where the act of seeing is also an act of looking into the past. Understanding this prepares the ground for the next layer of the challenge, where distance and time intersect with the relentless expansion of space itself, further reshaping what can be seen, what can be counted, and what must forever remain unknown. Light carries information, but it does not arrive unchanged. As it travels across the universe, it does more than simply move from point to point. The space it passes through changes, while the light is in transit. This change, this stretching of the very fabric of space-time, leaves an imprint on the light itself, pulling it, softening it, shifting it relentlessly toward longer, redder wavelengths. This effect is known as redshift, and it is one of the most direct, most profound observational clues in all of modern cosmology. Redshift is not something inferred from theory alone. It is measured directly, tangibly. When astronomers break the faint glow of a distant galaxy into a spectrum, they see familiar patterns, absorption and emission lines, the chemical fingerprints of hydrogen, oxygen, calcium. In nearby galaxies, these lines appear at their expected laboratory positions. In more distant galaxies, the same lines appear shifted, sometimes dramatically, toward the red end of the spectrum. The farther away the galaxy, the greater the shift. This observation tells a clear, inescapable story. The light has been stretched during its epic journey, not because the galaxy is simply speeding away through static space like a bullet, but because the space itself has expanded in the time between the emission of the light and its reception. The wavelength of the photon grows along with the universe. This stretching has immediate practical consequences for visibility. As light is stretched, its energy decreases. The same number of photons is spread across a longer wavelength, making the source appear dimmer, redder, and harder to detect. At great distances, this effect becomes severe, a thick veil drawn across the cosmos. Redshift therefore acts as an observational filter. It does not remove galaxies from existence, but it gradually, systematically removes them from our view. This understanding was not always accepted. In the early and mid-20th century, as the evidence for redshift mounted, astronomers explored alternative explanations, and some proposed that light might simply lose energy as it travelled across vast distances, a family of ideas sometimes grouped under the term tired light. Others suggested that redshift might arise from unknown interactions between light and the sparse matter floating in intergalactic space. These ideas were considered seriously, debated vigorously, because the implications of cosmic expansion were so profound, so unsettling. If the universe was expanding, then it must have been smaller, denser, hotter in the past. That raised unavoidable, monumental questions about origins, about a beginning, about the ultimate fate of everything. One of the most influential and elegant alternatives was the steady-state theory developed by Hermann Bondi, Thomas Gold, and Fred Hoyle. In this model, the universe expands, but maintains a constant average density through the continuous spontaneous creation of new matter. New galaxies form to fill the gaps left by expansion, so the large-scale appearance of the universe remains the same forever, with no beginning and no end. The steady-state theory was philosophically appealing, offering a kind of eternal, self-regulating cosmic equilibrium. And importantly for galaxy counting, it implied that galaxy populations were steady over time. If the universe were in a steady state, then the number of galaxies per unit volume would remain constant, unchanging. Observing farther into space would simply reveal more of the same. Older galaxies, yes, but galaxies statistically identical to those nearby. Galaxy counts would scale smoothly, predictably with distance, without dramatic changes in the types or numbers of galaxies. This made galaxy statistics a key testing ground, a battlefield of ideas. As observations improved, as surveys dug deeper, the predictions of steady-state models began to diverge starkly from reality. Deep surveys showed that distant galaxies were not simply more distant versions of nearby ones. Their properties changed unmistakably with redshift. Star formation rates were higher. Galaxy morphologies were more irregular, more chaotic. The universe looked younger, more violent, more active at earlier times. These changes were difficult, then impossible to reconcile with a universe that was eternally the same. The final, decisive blows came from multiple independent lines of evidence. The discovery of the cosmic microwave background radiation, the afterglow of a hot, though dense early say, and the detailed quantitative evolution of the galaxy populations revealed by the Hubble Space Telescope. The framework of an expanding universe with a hot, dense beginning, the Big Bang model, provided a far more natural, powerful explanation for all the data. Once expansion became the accepted, evidence-backed framework, redshift took on a new dual role. It became not just a measure of distance, but a measure of cosmic time, and a governor of observational limitation. As redshift increases, galaxies are pushed into regimes that challenge detection in every way. Their light moves out of the optical window and into the infrared. Their surface brightness plummets. Their features blur and soften. At sufficiently high redshift, even massive galaxies become faint red smudges, and small galaxies disappear entirely from view. No matter how hard we look, expansion does not hide all galaxies equally. It is a biased sensor. Compact, intensely star-forming regions, starbursts, can remain visible at great distances because their light is concentrated into a small brilliant knot. Diffuse extended systems, like the majestic spiral disks we see nearby, suffer far more. Their stretched light is spread so thin it falls below detection thresholds long before their more compact counterparts. This creates a selective, distorted view of the distant universe. Our observations preferentially reveal the brightest, densest, most extreme regions, while the extended, more tranquil structures fade away into the background noise. The farther back we look, the more incomplete and biased our census becomes. For galaxy counting, this is critical. And expansion means that detectability depends not only on a galaxy's intrinsic brightness, but on how that brightness is distributed, and on how far the light has travelled through an expanding medium. Two galaxies with the same total luminosity can have wildly different chances of being observed, depending on their size, their structure, their star formation, history. Expansion also introduces a practical moving horizon for observation. Beyond a certain redshift, galaxies are not just faint, they're effectively inaccessible to current instruments. Their light may exist, but it is too stretched, too weak, or shifted into wavelength bands that are difficult to observe from the ground or even from space. This horizon is not fixed. It advances as technology improves. Infrared telescopes extend our reach. Larger mirrors collect more precious photons. Better detectors reduce noise to a whisper. Each advance pushes the observable boundary outward. But the principle remains a law of cosmic observation. Expansion ensures that some galaxies will always lie just near or just beyond the edge of detectability, a perpetual frontier. As surveys deepen, new galaxies appear at this frontier, but the population just beyond the new limit remains hidden, an infinite regress of discovery. The steady-state debate highlights why this matters so deeply. If galaxy populations were static, missing galaxies would represent a finite correctable error, like missing pages in a book that could eventually be found. In an evolving, expanding universe, missing galaxies represent a moving target, a shifting baseline. The farther back we look, the more the population itself changes, and the harder it becomes to get a complete, unbiased sample. Expansion, therefore, shapes galaxy counts in two powerful, intertwined ways at once. It alters the appearance of galaxies through redshift and dimming, and it ensures that the universe we are observing is not the universe as it exists now, but a layered fossil record of its history. This dual effect complicates every estimate, introducing uncertainties that are not merely technical, but fundamental to the relationship between the observer and the cosmos. Counting galaxies is not like counting trees in a forest where all trees exist in the same present and are equally visible. It is more like trying to count waves on an ocean while the water itself is stretching, deepening, and changing its composition beneath them. The result is not confusion, but a necessary hard-won caution. Modern galaxy counts explicitly, meticulously account for redshift effects. They model how light is stretched. They correct for dimming. They estimate using statistics and simulations how many galaxies are likely missing at each distance bin. These corrections are grounded in observation and tested against data, but they carry intrinsic uncertainty. Expansion guarantees that uncertainty will never vanish entirely. What it also guarantees is that the universe revealed by our observations is filtered by time, by space, by the very dynamics of the cosmos. Redshift is not a nuisance to be corrected away. It is the fundamental mechanism that connects distance, time, and visibility into a single, coherent framework. And understanding this prepares the way for the next conceptual step, where expansion itself sets even deeper, more philosophical limits on what can ever be observed, on what a count can ever mean. No matter how advanced our instruments become, at a certain scale, counting galaxies one by one simply stops making sense. The sky contains too many objects, spread across too much volume, changing too subtly with distance and time. Even the most patient observer, armed with the largest telescope imaginable, could never compile a complete list by visual inspection alone. The problem is not a lack of effort or dedication. It is a problem of sheer, overwhelming scale. This is the moment where galaxy counting transforms from a task of identification into a branch of statistical inference. And it marks the transition from traditional observational astronomy to statistical cosmology. Statistical cosmology treats galaxies not as unique, individual wonders, but as members of populations, as points in a vast probability distribution. Patterns, distributions, averages, and variances become more important than any single example. The aim is not completeness in the everyday sense, not a list of every name, but representativeness, an accurate statistical description of the whole. Large-scale uniform surveys make this possible. One of the most influential of these is the Sloan Digital Sky Survey, SDSS, a long-running, monumental project that systematically mapped over a quarter of the sky using a dedicated telescope, uniform instruments, and meticulously controlled observing strategies. Rather than targeting pretty objects or known clusters, the survey scanned broad swaths of sky methodically, robotically, recording everything above its well-defined detection thresholds. This approach mattered enormously. Uniformity allowed astronomers to understand with precision what the survey was capable of detecting, and just as crucially, what it was likely to miss. Every limitation was documented, quantified, every sensitivity curve was measured, nothing was left to impression or guesswork. Calibration was the silent, unsung hero of this effort. Instruments drift over time, detectors respond differently to different wavelengths, atmospheric conditions vary from night to night, hour to hour. To correct for this, survey teams repeatedly observed standard stars, stars with known, stable properties, scattered across the sky. These celestial reference points allowed every raw measurement, every faint smudge, to be translated into reliable physical quantities, true brightness, accurate colour, precise position. Without such relentless calibration, comparisons across the sky would be meaningless. A galaxy appearing faint in one region might simply reflect a patch of bad seeing, or a thin veil of cloud, rather than an intrinsic property of the galaxy itself. Completeness is the next equally vital concern. A survey is said to be complete down to a certain brightness if it reliably detects all objects brighter than that limit within its coverage area. Below that limit, detections become sporadic, incomplete. Some objects are detected, others, identical in true brightness, are missed. Survey teams invest enormous effort in determining where this boundary lies. They sometimes inject artificial galaxies, with known properties, into their data streams to test their detection algorithms. They measure recovery rates. They painstakingly map detection probability as a function of brightness, size, colour, and surface brightness. The result is a completeness function, a mathematical description of the survey's blindness, a map of its limitations. This is where selection functions enter the picture. A selection function describes the probability that a galaxy with a specific set of intrinsic properties will be included in the final survey catalogue. It depends on everything: intrinsic brightness, distance, size, shape, colour, and that elusive property, surface brightness. It also depends on observational factors, atmospheric noise, instrumental resolution, the brightness of the sky background itself. No survey has a perfectly flat selection function. Some galaxies are easy, almost certain to be detected. Others are almost invisible to that particular set of eyes. Statistical cosmology works by modelling these biases explicitly, rigorously, rather than pretending they do not exist. Once the selection function is known, correction models can be applied. If a certain type of faint, diffuse galaxy is detected only 30% of the time at a given distance, then the observed number of such galaxies can be statistically adjusted upward to estimate the true number. If small galaxies are underrepresented because they are mistaken for stars, their expected contribution can be inferred from clustering patterns. This does not produce certainty. It produces a probability distribution, a range of plausible values. The language shifts decisively from counting to inferring. This approach may feel unsatisfying at first glance. There is no final, neat tally, no clean, definitive list, but it reflects the true, gritty reality of the problem. The universe does not present itself in a way that allows complete, unambiguous enumeration. Probabilistic counting acknowledges that limitation openly, honestly. It also allows different surveys to be combined, their strengths fused. Surveys covering different wavelengths, optical, infrared, radio, different depths and different areas of sky can be cross-calibrated. Their overlapping regions can be compared, discrepancies analysed to reveal hidden biases, agreements strengthening overall confidence. The Sloan Digital Sky Survey, for example, mapped millions of galaxies, providing an unprecedented statistical foundation for the nearby universe. Yet even this vast dataset captures primarily the brighter portion of the galaxy population. It is excellent world-class at counting luminous galaxies. It is less complete for the faintest dwarf galaxies, and for low-surface brightness systems that slip below its detection threshold. That limitation is not a flaw in the STS. It is a boundary condition, a statement of its capabilities. Later, deeper surveys build on this foundation by pushing to fainter limits, or by observing in wavelength regimes where different galaxy populations shine. Crucially, no single survey is treated as definitive. Modern galaxy counts emerge from the synthesis of many surveys, a consensus built from multiple independent lines of sight and methods. Models of galaxy populations are adjusted until they can reproduce the combined observations across all these datasets. Where the models fail, assumptions are revisited. This iterative process is slow, careful, and deliberately conservative. Uncertainty is not something to be hidden or eliminated. It is something to be quantified, embraced, and clearly reported. In statistical cosmology, uncertainty is structural. It arises from cosmic variance, the fact that different regions of the universe are not identical. A patch of sky might contain a rich cluster, while another patch of equal size might be an empty void. It arises from observational limits that cannot be removed by better technology alone. It arises from the evolving nature of galaxy populations and from the shifting definitions of what we count. Even if our instruments were perfect, the universe itself would introduce inherent variation. Surveys mitigate cosmic variance by covering large areas, but no survey can observe the entire sky to infinite depth. As a result, responsible galaxy counts are always expressed as ranges, as confidence intervals. Assumptions are stated explicitly in the fine print. This is not caution for its own sake. It is a faithful reflection of how the problem behaves. Counting by survey replaces the seductive illusion of completeness with a robust framework of measured uncertainty. It accepts that some galaxies will always lie below our detection thresholds. It acknowledges that the correction models we use rely on assumptions that may themselves evolve with better data. The alternative, to present a single precise number, would be to offer false confidence, a misleading simplicity. Astronomy has learned, sometimes through painful episodes, that such spurious precision often leads science astray. There is a quiet, profound elegance in this statistical approach. By embracing probability and uncertainty, astronomers gain robustness. Results can be updated, refined, as new data arrives without overturning the entire framework. Counts can rise or fall without implying that earlier scientists were wrong, only that our view has improved. In this way, large-scale surveys transform galaxy, counting from a fragile exercise, vulnerable to the next big telescope, into a resilient, cumulative enterprise. The numbers may change, but the methodological foundation remains sound, able to incorporate new knowledge. The universe is not being counted in the ordinary sense. It is being sampled, modelled, and understood statistically. That fundamental shift makes it possible to speak meaningfully about galaxy abundance at all, even in a universe where complete visibility is a theoretical impossibility. And it sets the stage for the next leap, the deep, targeted stares that push beyond the statistical limits of wide surveys, revealing populations that earlier surveys could only infer hint at or dream of. For decades, astronomers wondered what would happen if a powerful telescope simply stopped chasing interesting known objects and pointed instead at nothing. Not a galaxy cluster, not a bright nebula, but an apparently empty patch of sky, chosen precisely because it looked unremarkable. No prominent stars, no obvious galaxies, nothing that would normally justify precious hours of observing time. The Hubble Space Telescope, freed from the blurring effects of Earth's atmosphere, made that radical experiment possible. When the decision was made to point Hubble's eye at such a barren region and leave it there, not for minutes but for days, for over 100 consecutive orbits, the goal was not discovery in the traditional romantic sense. It was statistical. The idea was to sample the universe deeply but narrowly, to see what existed below the thresholds of all previous wide surveys, to measure how crowded space truly was when observed without prejudice, with the deepest patience we could muster. What emerged from that gamble would permanently, irrevocably, change our sense of cosmic abundance. As Hubble accumulated photon after precious photon over those long exposures, the empty patch of sky began to fill in, not with a few new objects, but with a multitude. Faint points appeared first, distant stars within our own galaxy. Then smudges. Then, as the integration continued, those smudges resolved into structured shapes. Tiny spiral arms. Compact elliptical blobs. Irregular, stretched forms. By the time the final image was processed, a staggering sight awaited. Thousands of galaxies were visible, in a region of sky no larger than a grain of sand held at arm's length. This was the Hubble Deep Field. Its power was not in any single spectacular galaxy. It was transformative because of the sheer, stunning density. In a microscopic pinprick of the heavens, Hubble had revealed a cross-section of the universe, a core sample of cosmic history, with galaxies stretching back billions of years, spanning a vast range of sizes, shapes, colours, and stages of evolution. The implication was immediate, overwhelming, and humbling. If thousands of galaxies existed in such a tiny random patch, then the total number across the entire sky had to be enormous, almost beyond comprehension. The deep field was not a special place. It had been chosen specifically for its ordinariness, its lack of known clusters or nebulae. There was no reason to expect an unusually high density of galaxies, which meant that the universe on average was far, far more crowded with galaxies than any previous estimate. Even the most generous statistical extrapolation from wide surveys had suggested. This was not guesswork. It was a direct, powerful statistical inference. Deep fields function as controlled, ultra-deep experiments. By observing a very small area to extreme depth, astronomers can measure the number of galaxies per unit area down to incredibly faint limits. That measured density can then be extrapolated, cautiously, to the entire sky. The word cautiously matters immensely here. Researchers dedicated to analysing deep field data focused not just on detection, but on interpretation. The challenge was not simply to count galaxies in a pretty picture. It was to understand which galaxies were being seen, which were still being missed due to redshift and dimming, and how representative this tiny, deep sample truly was of the cosmos at large. Deep fields are powerful because they reveal the faint, distant galaxies that wide, shallow surveys cannot possibly detect. But they are also narrow. They sample only a minuscule fraction of the sky. In such a small sample, cosmic variance becomes a serious concern. A single deep field might, by pure chance, pierce a slightly denser than average filament of the cosmic web, or a slightly emptier than average void. This could skew the apparent galaxy counts, making the universe seem richer or poorer than it truly is on average. This means deep fields cannot be treated as literal, perfect inventories. They are probes, exquisite core samples. By combining deep fields from different independent locations across the sky, the Hubble Deep Field North, the Hubble Deep Field South, later the Ultra Deep Field, astronomers reduce the risk of overinterpreting any single patch. Repeated experiments refine the statistics. Patterns emerge that are robust against local variation. What consistently emerged again and again was the same startling conclusion. The number of faint galaxies rose steeply, relentlessly, as the detection limit improved. There was no obvious cutoff, no point where the curve flattened, where the universe suddenly became sparse and empty. Each time Hubble looked deeper, with longer exposures or improved instruments, more galaxies appeared, fainter and redder than the last batch. This forced a fundamental rethinking of galaxy abundance. Earlier wide-field surveys had captured most of the light in the universe, but they had captured only a fraction of the galaxies. Deep fields revealed that a large, perhaps dominant, fraction of galaxies contribute very little to the total light budget. They are small, faint, and overwhelmingly numerous. This distinction is absolutely crucial. Counting light and counting objects are not the same task. The deep field galaxies often appeared irregular, messy, and compact, reflecting their youth and dynamism. Many were caught in the act of intense star formation, their blue knots shining fiercely. Some of these small, early galaxies would later merge to form the large systems we see today. Others would fade or be disrupted. The image was not a simple census of present-day galaxies. It was a layered archaeological record of galaxy formation and assembly across cosmic time. This introduced another complex layer of interpretation. When astronomers count galaxies in a deep field, they are counting galaxies as they existed at different epochs, all superimposed in a single image. Translating that 2D tapestry into a 3D timeline and then into an estimate of how many distinct galaxies exist today requires sophisticated modelling. Which of those early galaxies survive as distinct entities? Which merge? Which disappear? Extrapolation becomes a multi-step process of reconstruction. First, the observed number density is measured. Then, corrections are applied for detection limits and surface brightness dimming at different redshifts. Next, evolutionary models, informed by theory and simulations, are used to connect these early populations to the present-day population. Each step adds its own layer of uncertainty. None can be skipped. This is why deep field results are never quoted as simple, bold totals. They are expressed as ranges, often spanning an order of magnitude or more. The numbers are breathtakingly large, but they are not precise. Even so, the paradigm shift was unmistakable, irreversible. Before the deep fields, it was reasonable to hope that galaxy counts might eventually converge to a stable final value as surveys improved. After the deep fields, that comforting hope evaporated. The universe did not reveal a tidy end point. It revealed a population that kept growing, like a fractal, as sensitivity increased. The Hubble Ultra Deep Field, with even longer exposures, pushed this further, revealing galaxies fainter and more distant than ever before. Each incremental improvement in depth reinforced the same pattern. The faint end of the galaxy population was rich, extended, and showed no sign of truncation. This did not mean the universe contained an infinite number of galaxies within our horizon. It meant that previous counts, based on brighter samples, had been incomplete in systematic, profound ways. Deep fields also demonstrated, vividly, the importance of observing in different wavelengths. The iconic optical images captured only part of the story. Follow-up observations with infrared cameras on Hubble and other telescopes revealed additional galaxies whose light had been stretched completely out of the visible range by cosmic expansion. Multi-wavelength deep fields showed that different galaxy populations dominate different epochs. Again, the message was one of consistency, not chaos. The universe was richly structured, But that structure was layered, subtle, and revealed only when we looked in the right way, with the right tools. The deep field experiments did something else, equally important. They shifted the seat of confidence from individual, spectacular objects to statistical trends. No single galaxy in a deep field was, by itself, revolutionary. What mattered was the collective behaviour of thousands of them, the statistical distribution of their properties. This mindset aligns perfectly, naturally, with the probabilistic counting of statistical cosmology. Deep fields do not promise completeness. They promise depth. They offer a narrow, profound window into populations that are otherwise invisible to wide surveys. The limits of extrapolation from such a window remain. A single deep field cannot tell us about the statistics of the rarest, most enormous structures. It cannot fully sample the largest voids or the richest clusters. It cannot see galaxies beyond the observational horizon. But within those understood limits, it provides a powerful, direct constraint. Any model of the universe that predicts too few faint, distant galaxies fails immediately when confronted with deep field data. Any model that ignores the faint systems collapses under their cumulative weight. The deep fields made one thing unavoidable. The universe contains far more galaxies than anyone had seriously entertained when the counting began. Not because the universe changed, but because our tools finally became sensitive enough to reveal what had always been there, waiting in the deep dark. After Hubble's deep stares, galaxy counting could no longer rely on an intuition shaped solely by brightness and prominence. It had to account for the quiet, numerous, faint majority. That shift did not close the question of how many galaxies exist. It opened it wider than ever, grounding it in breathtaking observation, while making it clear that the answer would always depend on how deeply the universe was willing to be seen, and how honestly we were willing to interpret what we found. Some galaxies exist at the very edge of visibility, not because they are small, but because they are faint in a specific, profound way. They are not necessarily tiny in physical size. In fact, some are as wide as the Milky Way itself, spanning tens of thousands of light years. What makes them so difficult to see is not their extent, but their lack of concentration. Their stars are spread so thinly, so sparsely, that the collective glow they produce barely rises above the natural background glow of the night sky itself. These are the ultra-diffuse galaxies, and the broader class of low-surface brightness galaxies, systems that challenge almost every assumption we have about what a galaxy should look like. For a long time, these galaxies were effectively invisible, not because they were hidden at great distances, but because they were hiding in plain sight, camouflaged against the sky. Traditional surveys were designed, either explicitly or implicitly, to detect concentrated light, bright cores, sharp edges, high contrast. Diffuse systems fail on all these counts. Their light is smeared across large areas of the sky, making them easy to mistake for subtle gradients in the sky background, for instrumental artifacts, or for the faint, blurred wings of bright stars. This is why they were missed for decades, their existence only hinted at in the margins of data. Low-surface brightness galaxies are not rare oddities or cosmic failures. They are common, a fundamental part of the galactic ecosystem. They exist in all environments, in the lonely fields between clusters, in the outskirts of groups like our own, and even within the dense, violent cores of galaxy clusters. Some contain significant reservoirs of dark matter, their rotations betraying massive unseen halos. Others appear to be almost entirely dominated by it, with so few stars that they are essentially dark matter clouds, with a sprinkling of stellar tracers. Their discovery forced astronomers to confront a bias that had been baked into observational astronomy from the beginning. We are biased toward things that shine brightly per pixel. Astronomers like Peter van Dokkum played a central role in bringing these ghostly systems into focus, using innovative deep imaging techniques and painstaking data analysis that treated the sky background not as an annoyance to be subtracted, but as a signal to be meticulously modelled. His work helped identify large populations of ultra-diffuse galaxies in crowded environments like the Coma Cluster. These galaxies were astonishing not because they were exotic, but because they were ordinary in number, yet extraordinary in appearance. Some of these systems span tens of thousands of light-years, comparable to large spiral galaxies, yet contain only 1% or even less of the stars. If such a galaxy were placed in isolation near the Milky Way, it would be obvious, a vast, faint wraith. But at the distance of the Coma Cluster, its light is spread so thin it fades almost completely from view, becoming one with the darkness. This reveals a crucial, often overlooked point. Detectability is not governed by total luminosity alone. It is governed by how that luminosity is distributed in the two-dimensional plane of our detectors. Surface brightness is the key quantity here, and it is independent of distance in a way total brightness is not. A galaxy with its stars packed tightly into a small region produces a strong, concentrated signal against the background. A galaxy with the same total number of stars spread over a region 10 times larger produces a signal 100 times fainter per pixel. This effect becomes severe with distance. As galaxies recede, their already diffuse light is further dimmed by the expansion of the universe, and is spread across fewer and fewer detector pixels. Eventually, the signal becomes indistinguishable from the random noise of the sky. Ultra-diffuse galaxies sit precariously close to this boundary even when they are relatively nearby. At greater distances, they vanish from our view entirely, no matter how large they truly are. This explains why early galaxy counts underestimated their numbers so dramatically. Surveys that were highly successful at detecting compact galaxies, the brilliant spirals and ellipticals, were systematically, intrinsically blind to the diffuse ones. The universe appeared cleaner, more discrete, and simpler than it truly is. When detection methods improved, when astronomers learned to see the faintest gradients, the picture changed irrevocably. Deep imaging surveys, employing meticulous background subtraction and months of integration time on the largest telescopes, revealed that ultra-diffuse galaxies are widespread. In some massive galaxy clusters, they may outnumber the classic bright galaxies by a significant factor. In groups, they contribute a substantial fraction of the total population. Each new detection, each new catalogue of these ghosts, quietly but powerfully inflates the total galaxy count. This inflation does not come from discovering galaxies at the edge of the observable universe. It comes from recognizing galaxies that were always there, in our cosmic neighbourhood, but never registered as galaxies at all. They were the background. Low surface brightness galaxies also complicate classification in profound ways. Some appear red and dead, containing little or no ongoing star formation, their gas long since stripped away. Others host tiny, isolated pockets of young blue stars, like oases in a vast desert. Some are dominated by ancient stellar populations, their stars as old as the universe itself. Their histories are not uniform. What they share is a structural fragility. Diffuse galaxies are particularly vulnerable to environmental effects. In dense clusters, tidal forces from near misses with giant galaxies and the relentless pressure of hot intra-cluster gas can strip away their already tenuous stars and gas, making these galaxies even fainter over time. Some may survive for billions of years in this stripped, quiescent state. Others may be completely dissolved into elongated streams of stars, losing their identity as coherent galaxies altogether. This, again, raises thorny questions about counting. At what point does a galaxy cease to be a galaxy? When its stars are too spread out? When it loses the last of its gas? When its surface brightness falls below an arbitrary threshold? Different, equally reasonable answers lead to different totals. Luminosity bias, our innate and instrumental preference for bright, concentrated things, sits at the very heart of this problem. Human intuition and the early instruments built by humans favoured bright objects. Astronomers naturally, understandably, studied what stood out. What barely glowed was overlooked, dismissed, filtered out. This bias affects not only discovery, but the entire chain of interpretation. If the universe is sampled primarily through its brightest, most striking members, then those members shape our expectations. They become the prototypes. Our models are built around them. Our counts are extrapolated from them. The recognition of ultra-diffuse galaxies disrupts that entire approach. It reveals that brightness is not a reliable proxy for abundance. The most common type of galaxy, by some measures, may contribute very little to the total light of the universe. They hide in plain sight, not because they are far away, but because they are intrinsically faint. This has a direct, inescapable impact on estimates of how many galaxies exist. If a large fraction of galaxies are diffuse, then any count based primarily on compact, high-surface brightness systems will be incomplete. A census of the loudest voices that mistakes them for the entire crowd. Even the Hubble deep fields, powerful as they are, struggle to detect the most diffuse galaxies at moderate distances. Their light is too spread out, their signal too integrated with the darkness. Corrections for this missing population must be applied statistically. Models must assume the existence and properties of galaxies we cannot observe directly in deep fields. Each such assumption adds another layer of uncertainty. But ignoring these systems adds a far more dangerous thing: bias. There is a quiet, profound irony here. Ultra-diffuse galaxies are large. They are not small remnants or minor curiosities. They are full-scale galaxies that simply failed to shine efficiently, to condense their stars into a brilliant nucleus. In a sense, they represent an alternative, equally valid outcome of galaxy formation, one where dark matter dominates the gravitational potential, and star formation proceeds with tragic inefficiency, sputtering out before it can light up the halo. Their existence broadens, democratizes, the concept of what a galaxy can be. They also reinforce the recurring theme with the force of a hammer blow. The universe contains many, many more galaxies than it appears to at first, or even second glance. Not because galaxies are hiding at unimaginable distances, but because a huge number of them emit their light reluctantly, whispering where others shout. Counting galaxies, therefore, becomes an exercise in humility, a constant correction for the limits of our own perception. Each improvement in sensitivity, in data processing, reveals systems that challenge our previous assumptions. Each new category of faint object widens the population. Ultra-diffuse and low-surface brightness galaxies ensure that the total number of galaxies continues to rise as our detection methods improve. They remind us, forcefully, that the universe does not optimize itself for our visibility. It simply is. And much of it, it turns out, barely glows at all. Much of the universe's structure, the very framework upon which galaxies are built, is shaped by something that emits no light, no radio waves, no signal we have yet been able to capture directly. Galaxies form, grow, and survive inside vast, invisible concentrations of dark matter. These concentrations, known as dark matter halos, provide the gravitational scaffolding, the deep potential wells, that allow ordinary gas to collect, cool, and eventually fragment into stars. Without these halos, galaxies, as we know them, would not exist. Yet, dark matter itself remains enigmatic, detectable only through its gravitational influence on the things we can see, the motions of stars, the bending of light, the dynamics of whole clusters. This invisibility introduces a powerful, fundamental complication when we try to count galaxies. Astronomers do not observe dark matter halos directly. They observe stars, gas and dust, the luminous tracers, and then infer the presence and properties of the halo from how those visible components move and cluster. This means every visible galaxy is understood to be the bright tip of a much larger, unseen iceberg. Halo occupation models formalize this critical idea. These models describe, in statistical terms, how galaxies of various types and luminosities populate dark matter halos of different masses. In simple terms, they ask, in a halo of a given mass, how many galaxies tend to live, and what are their properties? How are those galaxies distributed within the halo? Is there a central giant, surrounded by satellites? This approach allows astronomers to connect what we see, galaxy clustering, brightness distributions, to the underlying theory of dark matter structure formation. This is where supercomputer simulations enter the story, not as mere illustrations, but as theoretical laboratories. Large cosmological simulations, with names like Millennium, Illustris and Eagle, attempt to recreate the evolution of cosmic structure from the first tiny ripples after the Big Bang to the present day. They begin with initial conditions informed by observations of the cosmic microwave background and allow the laws of gravity, coupled with models for gas physics, to dictate what emerges. These simulations do not draw galaxies by hand. They let them form naturally from the collapse of matter under gravity. The backbone of these simulations is dark matter, represented by billions of simulated particles that trace the growth of the cosmic web. As the simulation evolves, these particles clump together, forming halos, subhalos, and filaments in a beautiful, complex dance. Once this dark matter skeleton is in place, ordinary matter, baryons, is added. Gas follows the gravitational pull of the dark matter, flows into the halos, cools, collapses, and under the right conditions forms stars. Over time, galaxies emerge within the simulated universe, with their own histories of mergers, star formation, and quenching. Visionaries like Volker Springel have been central to developing these computational approaches, pushing the limits of what can be simulated, striving to incorporate more realistic physics into ever larger volumes. His work helped demonstrate that it is possible to reproduce many of the statistical properties of the observed universe: the galaxy luminosity function, the colours, the large-scale clustering, using physically motivated rules. This provides a powerful check on our understanding. These simulations are not small endeavours. They often track billions of particles across volumes hundreds of millions of light-years wide. They require vast computational resources, running for months on the world's most powerful supercomputers. Each run produces petabytes of data that must be sifted, analysed, and compared to observations. Despite their staggering sophistication, these simulations face an unavoidable, fundamental limitation. They cannot resolve everything. The processes that govern star formation, supernova explosions, black hole feedback, and gas turbulence occur on scales far, far smaller than the resolution limit of even the largest simulations. It is computationally impossible to calculate these processes from first principles at every point in a simulated universe the size of our own. Instead, simulations rely on what are known as subgrid models. These are recipes, informed by detailed observations and by smaller, high-resolution simulations, that describe how small-scale physics behaves on average within a larger simulated cell. They specify, for example, how efficiently gas turns into stars under certain conditions of density and temperature, or how much energy a supernova injects into its surroundings, or how a growing black hole affects its host galaxy. These choices matter enormously. Changing a subgrid prescription, adjusting the efficiency of star formation or the strength of stellar winds, can alter the number of galaxies that form, their masses, their brightness, and their survival rates. Small changes at the microscopic subgrid level can ripple outward, reshaping the entire macroscopic population of simulated galaxies. This introduces a fundamental humility into simulation-based counting. When a simulation predicts a certain number of galaxies above a given mass, that number reflects both the underlying laws of physics and the specific assumptions and approximations embedded in the subgrid model. Agreement with observation is meaningful, encouraging, but it is not absolute proof that the model is uniquely correct. Disagreement is informative, not necessarily a failure. It points to where our understanding of the small-scale physics is incomplete. What matters most is the pattern, the broad strokes. Modern simulations successfully reproduce many large-scale features of the universe. They match the way galaxies cluster, the cosmic web of filaments and voids. They reproduce the rough distribution of galaxy masses and luminosities. They capture the emergence of elliptical galaxies in dense environments and spirals in the field. When simulations and observations agree on these broad trends, confidence grows that the underlying framework, gravity, dark matter, cosmic expansion, is sound. At the same time, tensions remain, and they are illuminating. Some simulations predict more small, faint galaxies than we observe around the Milky Way, a modern incarnation of the missing satellites problem. Others struggle to reproduce the exact number of very massive, quiescent galaxies at certain epochs. The precise balance between gas cooling, which fuels star formation, and feedback, which shuts it off, remains an active, vibrant area of refinement. These tensions are not embarrassing, they are productive. They highlight exactly where our understanding is incomplete. They point to physical processes we may be missing or misrepresenting. They guide the design of new, more sensitive observations and motivate improved, more physically grounded models. From the perspective of galaxy counting, simulations serve a specific vital role. They provide a way to estimate populations that cannot be observed directly, especially the faintest, smallest galaxies at all epochs, and the galaxies that may have formed and been destroyed early on. They suggest how many galaxies should exist below our detection thresholds, based on our best current theories. They predict how galaxy numbers should change with time and environment. But they do not, and cannot, replace observation. A simulated galaxy is not a detection. It is a hypothesis about what should exist given a set of assumptions. Observations test those hypotheses. When the two diverge, the assumptions are revisited, the models tuned. This back-and-forth dialogue between simulation and observation is central to modern cosmology. It ensures that galaxy counts are not extrapolated blindly into the unknown. They are constrained by data at every step, with simulations used cautiously to explore the regimes where data is sparse or absent. There is a deeper lesson here as well. Simulations reveal that the universe naturally produces complexity and diversity. Even starting from simple, almost smooth initial conditions and governed by well-understood laws of gravity, the outcome is rich, varied, and exquisitely sensitive to initial conditions and small-scale physics. Galaxy populations are not fine-tuned to simplicity. This reinforces why galaxy counts resist neat, precise answers. The universe does not contain a neat, evenly spaced collection of identical units. It contains a hierarchy of structures shaped by chance encounters, chaotic feedback loops, and environmental effects that vary from place to place. Simulations capture this beautiful messiness. They do not eliminate it. When astronomers quote estimates for the total number of galaxies, they often rely on simulations to help fill in the faint end of the population, the part forever below our observational horizon of sensitivity. But they do so with explicit caveats. The numbers are conditional. They depend on how star formation behaves in the smallest, lowest mass dark matter halos. They depend on the efficiency of stellar feedback in ejecting gas. They depend on how galaxies respond to the ionizing radiation from the first stars and quasars. All of these dependencies are areas of vibrant, ongoing research. Pioneers in the field have emphasized that simulations are tools for understanding, not oracles. They help us explore possibilities, clarify relationships between cause and effect, and expose the sensitivities of the cosmic system. They also remind us of our limits. No simulation can capture every detail. No model can include every physical process at full resolution. There will always be uncertainty at the smallest scales, and those uncertainties propagate upward, leaving an imprint on the large-scale statistics we care about. This does not undermine the value of simulations. It defines their proper use. By comparing simulated universes to the real one, astronomers learn which assumptions are reasonable and which are not. They learn where confidence is warranted and where caution is required. In the context of galaxy counting, simulations provide a vital complement to observation. They help bridge the gap between what we can see and what likely exists. But they do not deliver a final authoritative number. Instead, they reinforce a pattern that has emerged again and again throughout this story. Every time the universe is examined with greater depth, with broader scope, or with more sophisticated theoretical tools, it reveals more structure than we previously expected. Not because it is deceptive, but because it is generous, almost inexhaustible in its complexity. Simulating a universe full of galaxies does not simplify the counting problem. It deepens it, adds layers of nuance. And in doing so, it reminds us that understanding cosmic abundance is less about reaching a final closure, and more about endlessly refining our perspective, questioning our assumptions, one galaxy, one halo, one simulation at a time. At some point, the question subtly shifts. It stops being how many galaxies exist in principle, in the grand sweep of theory, and becomes how many can actually be observed today, with the light that has reached us, within the limits of our instruments and our definitions. This distinction is not just philosophical, it is practical, and it matters deeply. The observable universe is not defined by our imagination or by the extrapolations of theory, but by the light that has had time to reach us since the beginning, and by the tools we have built to catch that light. Within those hard physical limits, astronomers attempt to estimate how many galaxies are present right now, acknowledging that any answer is provisional, conditional, and a snapshot of our current understanding. Modern observational studies, synthesizing deep fields, wide surveys, and theoretical constraints, tend to converge not on a single number, but on large, overlapping ranges. Depending on how faint a system must be to qualify as a galaxy, and how aggressively corrections are applied for unseen populations, estimates for the number of galaxies within the observable universe typically span from 200 billion to 2 trillion. This vast spread is not a sign of fundamental disagreement about the basic facts of the universe. It reflects honest methodological differences. Some studies focus on counting galaxies directly detected in the deepest Hubble images, then extrapolating cautiously to the full sky, accounting for what Hubble might be missing at the very faintest end. Others incorporate results from large cosmological simulations and halo occupation models, using the observed clustering of bright galaxies to infer the vast legions of faint ones that must surround them to produce that clustering pattern. Each approach rests on a different set of assumptions about galaxy formation, survival, and detectability. Researchers who specialize in synthesizing these approaches have been central in shaping our modern view. Their work has emphasized a key insight: sensitivity drives the count. As telescopes become more sensitive, they do not simply refine an existing number, they reveal entirely new populations that were previously below the noise. Each improvement in depth uncovers galaxies that were, for all previous intents and purposes, invisible, especially at the low mass, low surface brightness end of the spectrum. This creates a predictable historical pattern. Galaxy counts rise as surveys deepen. They do not plateau cleanly. The curve of discovery has no obvious knee. The reason lies in the mathematical shape of the galaxy luminosity function. Bright galaxies are rare. Faint galaxies are overwhelmingly common. The number of galaxies increases steeply as a power law as intrinsic brightness decreases. Missing even a small range at the faint end, due to instrumental limits, can therefore exclude a vast number of galaxies from the count. Early surveys captured most of the light in the universe, emanating from the rare bright beasts. Modern surveys push deeper, capturing more of the population, the numerous faint dwarfs and diffuse ghosts. But still not all of it. There is always a frontier. Different surveys also probe different slices of the electromagnetic spectrum, and each slice reveals a different facet of the population. Optical surveys excel at detecting galaxies with active, unobscured star formation. Infrared surveys, like those from Spitzer and Webb, reveal dust-obscured galaxies and systems whose light has been redshifted out of the optical. Radio observations trace gas-rich galaxies that might be faint in starlight. No single survey captures the full diversity. Combining these datasets requires Herculean efforts in cross-calibration. An object blazing in the infrared might be a dim speck in the optical. Selection functions differ. Corrections must be applied consistently across wavelengths. Even with all this care, uncertainty remains, woven into the fabric of the result. Cosmic variance plays its stubborn role. A single deep field, for all its depth, may sample a region that is slightly over-dense or under-dense compared to the true cosmic average. Large area surveys, like those from the Sloan Digital Sky Survey, reduce this effect by covering huge swaths of sky, but they cannot reach the same depth. There is a fundamental trade-off between depth and area, and both are needed to beat down uncertainty. There is also, always, the issue of classification, that grey area we keep returning to. Some of the faintest systems detected hover near the boundary between ultra-faint dwarf galaxies and large, puffed-up star clusters. Including or excluding them changes the count. Reasonable, careful researchers can look at the same data, the same smudge of light, the same noisy spectrum, and make different, defensible classification choices. Neither is obviously wrong. They are applying different thresholds, weighting different pieces of evidence. When modern studies quote numbers on the order of 1 trillion galaxies, they are not claiming to have counted each one, like beans in a jar. They are stating that, given the totality of current observations and our best models, this is the most plausible range for how many galaxies exist within the observable universe today. The phrase "within the observable universe" is doing critical work here. It excludes galaxies beyond our causal horizon, which cannot be seen or counted by any means. It also excludes dark matter halos that never manage to light up with stars, which are not classified as galaxies under any standard definition. Within those bounds, the uncertainty is not trivial, but it is constrained, quantifiable. The lower end of estimates, around 200 billion, corresponds to conservative assumptions, counting only galaxies we are very confident about, with minimal extrapolation into the unknown faint end. The higher end, 1 trillion or even 2 trillion, assumes that many small, diffuse and ultra-faint galaxies remain undetected even in our deepest surveys, consistent with the predictions of our most successful simulations and with the steady trickle of new dwarf discoveries in our local group. What is striking in the end is not the exact digit in the trillions place. It is the scale, the order of magnitude. Even the most conservative modern estimates place the number of observable galaxies far, far above what anyone imagined a century ago, or even 50 years ago. The universe is not sparsely populated with a few majestic systems. It is teeming, crowded, bustling with vast numbers of modest ones. This conclusion is robust, echoing across methods. Whether one starts from the density of galaxies in the Hubble Deep Field, from the shape of the luminosity function measured by the Sloan survey, or from the predictions of cosmological simulations informed by both, the same qualitative picture emerges, again and again. Galaxies are abundant. Faint galaxies dominate the numbers. Detectability, not existence, is the primary limiting factor in our census. This is where we arrive at a kind of conditional certainty. Astronomers are confident about the trends, the distributions, the broad brushstrokes. They are confident that galaxies number in the hundreds of billions at the very least. They are less confident about the exact total, and they are honest about that too. That imbalance is appropriate, scientific. The data support broad, powerful conclusions, not a precise inventory. When the number changes from hundreds of billions to trillions, it is not because earlier work was wrong. It is because new sensitivity, new wavelengths, new models have revealed new populations, forcing a revision, an expansion of our understanding. This process will continue. It is the engine of science. Future telescopes, like the Nancy Grace Roman Space Telescope, will push detection limits further in wide fields. New surveys will reveal galaxies even fainter and more diffuse than those we know today. The counts will rise again, not because the universe has changed, but because our view has improved, because we have learned to see a little more of what was always there. So, how many galaxies can be observed today? The honest answer, the scientific answer, is a range, not a figure. A range grounded in observation, constrained by theory, and shaped by the very real physical limits of detection. Within the observable universe, there are at least 200 billion galaxies, and very likely many times that number, perhaps 1 trillion, perhaps more. The exact total depends on how faint one is willing and able to look, and on where one draws the line around the word galaxy. That uncertainty is not a weakness of the science. It is a reflection of how the universe presents itself to a creature living inside one galaxy at one moment in time, using telescopes built by hand. The universe is generous with structure, but selective with visibility. And every time our sensitivity improves, it reminds us with gentle insistence that abundance was never the limiting factor in our understanding. Only perception was. The arrival of the James Webb Space Telescope did not rewrite the story of galaxy counting. It sharpened it, deepened it, added finer lines to a picture that was already coming into focus. From the beginning, Webb was designed to see what earlier telescopes could not, to push into the infrared with sensitivity and resolution that were not just an improvement, but a revolution. Its strength lies in its ability to catch light that has been stretched far beyond the visible range by cosmic expansion, light from the earliest epochs of structure formation. This makes it the ultimate tool for observing the infant universe, for catching galaxies in the act of being born. Before Webb, much of that first billion years was inferred rather than seen, hinted at by a handful of extremely red, extremely faint blobs at the limits of Hubble's vision. Their properties were uncertain, their numbers poorly constrained, their very nature a subject of debate. Webb changed the balance of evidence by observing in the infrared not just with more sensitivity, but with a clarity that allowed these distant smudges to be studied as galaxies, not as statistical anomalies. Webb revealed galaxies that had previously slipped below every detection threshold. Many of these systems are faint, compact, and, critically, surprisingly numerous. They appear at redshifts when the universe was only a few 100 million years old, a period once thought to be dark, quiet, and sparsely populated with the first struggling stellar systems. Webb showed it was anything but. These early observations did not come from a single dramatic press release image, though those images captured the public imagination. They emerged from the careful, patient, sometimes dry work of multiple research teams working independently, comparing data across different deep fields, calibrating measurements against models, and testing assumptions against reality. The emphasis was not on spectacle, but on consistency, on reproducibility. What these teams found was not chaos, but a startling continuity. The early universe appears rich in small star-forming galaxies, just as the broad brushstrokes of hierarchical formation models had long predicted. Webb did not suddenly reveal a universe overflowing with unexpected, fully formed giants from the dawn of time, though it did find some surprisingly massive and evolved systems that have spurred healthy debate. Instead, it began to fill in the faint end of the population at the highest redshifts, revealing systems that were always expected to exist, but had never before been observed directly. This matters profoundly for counting. Webb does not allow us to count all galaxies directly. It does not eliminate observational horizons or bypass surface brightness dimming. What it does is tighten constraints. It reduces the gap between what is observed and what is inferred at the most distant, most challenging epochs. By detecting galaxies at earlier times and lower luminosities than ever before, Webb improves our estimates of how many galaxies formed in the universe's first chapters. Those estimates, in turn, inform and refine the models we use to understand how many of those early galaxies survive, merge, and contribute to the population we see around us today. The revisions are indirect but significant. When Webb reveals that faint galaxies are more common at high redshift than our previous best measurements suggested, it tells us that earlier surveys, even Hubble's, underestimated the sheer fecundity of the early universe. That does not automatically increase the present-day galaxy count by a simple multiplier, but it changes the inputs fed into our models of galaxy evolution. More early galaxies imply a more active merger history, more hierarchical growth, and potentially more stellar debris, more faint streams and diffuse halos, embedded within today's massive galaxies. It also suggests that a greater number of those early small galaxies might have somehow persisted quietly in the outskirts of groups, surviving to the present day as ultra-faint dwarfs, contributing to that quiet, numerous population. Webb also clarifies, with stunning sharpness, the role of wavelength in detection. Many of the first galaxies emitted most of their light in the ultraviolet, from their hot, young stars. By the time that light travels over 13 billion years to us, it is stretched deep into the infrared. Optical telescopes like Hubble simply could not see it. It was absent from their view. This did not mean those galaxies were invisible in principle. They were invisible to a specific set of eyes. Webb's infrared vision reveals the population that bridges the gap between theory and observation at these early times. It confirms that early galaxy formation was not a rare special event, but an efficient, widespread process, as common as gravity and cooling gas could make it. At the same time, Webb reinforces our familiar, humbling limitations. Even with its breathtaking sensitivity, Webb observes only tiny regions of sky in extreme depth. It does not provide an all-sky census. Cosmic variance, the chance that its deep field might land on a particularly rich or poor patch of the early universe, remains a very real concern. Some deep fields appear richer in early galaxies than others. Statistical interpretation, the weighing of probabilities, is still required. Webb's discoveries, therefore, feed directly into the same probabilistic, model-dependent framework established by Hubble deep fields and wide surveys. They do not replace it, they enrich it. The difference lies in the confidence of our inferences. With Webb, astronomers are less reliant on sheer extrapolation at the highest redshifts. They can measure luminosity functions, galaxy sizes, and stellar masses more directly, even at these incredible distances. They can begin to observe the shapes and structures of galaxies in the first billion years, rather than inferring them from a handful of pixels. This reduces uncertainty at one crucial end of the cosmic timeline, the beginning, while leaving other uncertainties, those about the middle chapters of galaxy evolution, intact. Webb has also revealed that some early galaxies appear more massive, more chemically evolved, and more structured than the simplest models predicted for their age. These findings sparked initial headlines about universe-breaking galaxies, but careful follow-up analysis has largely shown they remain consistent with revised models of rapid, efficient early star formation, rather than requiring a fundamental overthrow of cosmology itself. This pattern is deeply instructive. Webb does not overturn existing frameworks. It refines them. It exposes where our assumptions were too conservative, where our models needed more flexibility. It highlights where adjustments are needed, not where abandonment is required. For galaxy counting, this means that estimates continue to rise at the margins, in a controlled, understood way, rather than jumping discontinuously. The universe revealed by Webb is richer, more detailed, more surprising in its particulars, but it is not alien. It is the same universe, seen with new eyes. There is an important psychological shift here, one that speaks to the maturity of the field. Public discussion often frames new telescopes as revolution machines, poised to demolish old ideas and start from scratch. In practice, in a mature science like cosmology, progress is more often incremental, a relentless honing. Webb's most solid results sit comfortably within the trajectory established by decades of deep fields, simulations, and statistical surveys. Each new population it discovers was anticipated in some form by theory. Webb simply makes it visible, real, measurable. This continuity matters because it reinforces trust in the methods we use to estimate cosmic abundance. When new magnificent instruments confirm rather than contradict the broad picture, confidence in the underlying framework grows. The broad picture is this. Galaxies are numerous. Faint galaxies dominate by number. The early universe was abundant with small star-forming systems. Many of these merged to build the giants we see today. Some survived as faint relics. Detection limits, not existence, set the boundaries of our observation. Webb strengthens every part of that picture. It does not answer the question of how many galaxies exist with finality. It narrows the uncertainty. It improves our calibration. It reveals populations that push our counts upward in controlled, quantifiable ways. Future analyses will incorporate Webb's torrent of data into our luminosity functions, our merger tree models, our halo occupation distributions. Estimates will be revised again. The numbers may increase slightly. The confidence ranges may tighten, but the character of the answer will remain the same. There will still be a range, not a point. There will still be assumptions about the faintest fringes. There will still be galaxies hovering below our newest, deepest detection thresholds. What Webb changes is not the nature of the uncertainty, but the scale of our confidence. The universe appears once again to be generous with galaxies and astonishingly consistent with its own long, unfolding history. Webb does not close the book on galaxy counting. It adds more pages, written in finer detail, with richer illustrations, without changing the fundamental direction of the story. And that is perhaps its most profound contribution. It shows that deeper vision does not simplify the universe. It reveals it more fully, in greater complexity, while preserving the quiet, essential truth that no matter how far our instruments reach, some structure will always remain, tantalizingly, just beyond the edge of sight. There comes a point, a sobering and clarifying point, where the question is no longer about what we have missed, but about what we can never see. Not because our telescopes are insufficient or our surveys incomplete, but because the structure of the universe itself, the geometry of space-time, and the history of expansion sets absolute, impassable limits on observation. These limits are not technological, they are causal, woven into the fabric of reality. The universe has a finite age, about 13.8 billion years. Light travels at a finite, unbreakable speed. Together, these two simple facts define a boundary known as the particle horizon, or the cosmic light horizon. It marks the greatest distance from which light has had time to reach us since the beginning of cosmic expansion. Anything beyond that boundary has not yet had the opportunity to send us a signal, a photon. Its light is still in transit, or will forever be receding from us. This horizon is not an edge in space, a wall of bricks. It is an edge in time, a limit set by the history of the cosmos. Galaxies beyond it may exist. They are almost certainly numerous. They may resemble the galaxies we see nearby, or they may differ in ways we cannot even conceive. What matters is that their light has not arrived, and depending on the precise details of cosmic expansion, that light may never arrive, no matter how long we wait. This introduces a critical foundational distinction. Some galaxies are unseen because they are too faint, too diffuse, or hiding behind dust for our current instruments. These galaxies are unseen, but reachable, with better sensitivity, longer stares, different wavelengths. Many of them can and will be revealed. They are part of the observable universe, just below our current threshold. Other galaxies are unreachable. They lie beyond the causal horizon, in regions of space whose light has not reached Earth, and due to the accelerating expansion of the universe, whose future light may never do so. These regions are not hidden behind an obscuring screen. They are separated from us by the fundamental architecture of space-time, by the fact that the space between us is expanding faster than light can bridge it. They are, in a very real sense, in a different universe, causally disconnected from our own. This distinction matters deeply for how we interpret galaxy counts, and for the meaning of any number we quote. When astronomers estimate how many galaxies exist, they are careful, precise, and rigorous in specifying that the count applies to the observable universe. This is not a philosophical caveat or a hedging of bets. It is a physical, empirical constraint. The observable universe is the portion of the cosmos that can, in principle, be studied using light or any other signal limited by the speed of light. Beyond it lies more universe, likely a vast amount, but not more data. It is forever outside our empirical grasp. It is tempting, a natural human impulse, to ask what lies beyond the horizon. It is equally tempting to extrapolate to assume it's more of the same. If the observable universe, a sphere 93 billion light-years in diameter, contains 2 trillion galaxies, then perhaps the unobservable regions contain trillions more, ad infinitum. This may be true, many cosmological models suggest it is, but science must proceed with disciplined caution here. The laws of physics appear uniform across the entire observable universe. The cosmic microwave background is stunningly isotropic. Large-scale structure shows statistical homogeneity when averaged over sufficiently large scales. These observations support the cosmological principle, the idea that, on the largest scales, the universe is roughly the same everywhere. This principle gives us reason to think that regions beyond our horizon are not fundamentally, bizarrely different. Even so, this remains an inference, an assumption guided by data from within our horizon. It is not, and can never be, an observation. There is a critical difference between extending a well-tested pattern within our observed domain and claiming certainty about what lies forever beyond our causal reach. The former is a necessary, controlled assumption that allows science to function. The latter is speculation, however plausible. For this reason, responsible astronomers avoid definitive statements about the total number of galaxies in the entire universe. They restrict their claims to what can be observed, modelled, and constrained by data that has actually reached us. This restraint is not a lack of imagination or courage. It is methodological discipline, the very core of empirical science. Causal horizons also evolve over time, adding another layer of subtlety. As the universe ages, light from more distant regions has more time to reach us. The observable universe grows, but only slowly, and not without limit. Galaxies that were once beyond our horizon gradually become observable, not because they move, but because time allows their ancient light to finally complete its journey. At the same time, cosmic acceleration introduces a competing, counterintuitive effect. Some regions of space are already receding from us so rapidly that light emitted from them today will never reach us in the future. Those regions lie beyond what cosmologists call the event horizon. They are not merely unobserved, they are permanently, irrevocably inaccessible. This creates a profound asymmetry. The observable universe grows, but its growth has an asymptotic limit. There are regions that will remain forever outside our observational domain, no matter how far into the future we wait. Galaxies within those regions can never be counted, catalogued, or confirmed by us. They are not missing data points in a solvable puzzle. They are inaccessible in principle. This is why careful scientific discussions of cosmic abundance stop where observation stops. They do not invoke infinity casually. They do not indulge in untestable speculation about what lies beyond the causal limits. They acknowledge, clearly, what is known, what is inferred with confidence, and what is fundamentally, permanently unknowable from our location in space and time. This approach preserves intellectual clarity and scientific integrity. Unseen galaxies within the observable universe represent an incomplete census. They are a challenge, a motivation for building better telescopes, designing deeper surveys, and developing sharper models. They represent future work, future discovery. Unreachable galaxies, those beyond the horizon, belong to a different category altogether. They do not motivate better instruments. They motivate a quiet, profound humility. They remind us of our place. It is also important not to conflate size with reach. The observable universe is already unimaginably vast. Its diameter is nearly 100 billion light-years. Within that sphere, there is room for extraordinary numbers of galaxies, for complexity that will take centuries to unravel. The fact that some regions are forever beyond reach does not diminish the staggering richness of what we can study, nor does it imply that our observable universe is atypical, a special or privileged place. All available evidence suggests it is a fair sample, a random patch of a larger, statistically uniform whole. But this too remains an assumption, a well-motivated, parsimonious, and successful assumption. But an assumption grounded in the data we have, not a demonstrable fact about the entirety of existence. Avoiding infinity claims is part of this disciplined approach. Statements about infinite numbers of galaxies sound grandiose, but they do not arise from measurement. They arise from extrapolating a pattern beyond the domain where we have evidence to support it. In science, such untestable statements are treated with caution, set aside. The universe may be infinite in extent. It may be finite but unbounded, like the surface of a sphere. Current observations, from the flatness of space-time to the patterns in the cosmic microwave background, cannot decide this question conclusively. They are consistent with a universe that is vastly larger than what we see, perhaps infinitely so, but they do not prove it. What can be said with confidence, with the full weight of modern cosmology behind it, is this: Within the observable universe, there are vast numbers of galaxies, far more than early astronomers ever dreamed. Their abundance is supported by multiple, independent, converging lines of evidence. Their diversity is well documented. Their distribution follows understandable patterns shaped by gravity, dark matter, and time. Beyond the observable universe, there is a necessary, respectful silence. Not an emptiness, but an absence of information. A blank space on the map, not because it's empty, but because the map cannot be drawn. This silence is not a frustration, it is a clarification. It draws a bright, clear boundary around what science can responsibly address with evidence. It reminds us that some questions do not have answers, not because the answers are mysterious, but because the questions themselves lie outside the realm of empirical inquiry. Counting galaxies, therefore, is not about reaching for the absolute, for an all-encompassing total. It is about describing what can be known within the limits set by nature itself. The observable universe offers more than enough wonder, more than enough mystery, more than enough structure to occupy generations of curious minds. Beyond it lies a continuation we may hypothesize about, but can never confirm. Maintaining that distinction allows our galaxy counts to remain grounded, meaningful, and honest. It also reframes the original, seemingly simple question. How many galaxies are there? Within our causal reach, the answer is vast, conditional, and ever-improving. Beyond our reach, the only scientifically responsible response is a disciplined, and in its own way beautiful, restraint. At the end of all the surveys, the simulations, the deep fields, the revisions, the number itself can begin to feel almost misleading. Hundreds of billions. Trillions. These are quantities that stretch language, that become abstractions. It is tempting, deeply tempting, to treat these figures as the answer, as if the entire goal of this centuries-long endeavour were to land on a single authoritative total to put in a textbook and be done with it. But that has never really been what galaxy counts are for. The number does not represent a final inventory. It represents a description, a snapshot of our current understanding. Every estimate of how many galaxies exist is inseparable from the method used to obtain it. Change the depth of the survey, and the number changes. Change the wavelength of observation, and the number changes again. Adjust the definition of what qualifies as a galaxy, and the total shifts, sometimes dramatically. This is not a flaw in the process. It is the process. Galaxy counts are method-dependent descriptors. They summarize what a particular combination of instruments, assumptions, models, and corrections reveals about the universe at a particular moment in the history of science. They are statements about visibility, about classification, about inference, not declarations of absolute, timeless fact. This is why ranges, probabilities, and confidence intervals replace exact totals in the serious literature. When astronomers report that there are likely between 200 billion and 2 trillion galaxies within the observable universe, they are not hedging their bets. They are being precise in the only way the problem allows. The range captures an uncertainty that cannot be eliminated without pretending to know more than our observations permit. Exact numbers imply a closure that the universe does not offer. Ranges acknowledge the limits that are not just technological, but epistemic. There are limits to what can be known, even in principle, about a universe observed from a single location, at a single moment in cosmic time, using light that arrives with delays of billions of years. Some galaxies are too faint to ever be detected from our vantage point. Some existed only briefly before merging away. Some lie in regions of space that are forever receding beyond our causal grasp. No improvement in instrumentation, no leap in engineering, can fully erase these fundamental constraints. This does not mean our knowledge is shallow or feeble. It means it is conditional, contextual, and robust within those conditions. Galaxy counts depend on our definitions of galaxies, on our models of cosmic evolution, on our corrections for what we cannot see, and on our assumptions about what lies just below our detection thresholds. Each of these elements is grounded in evidence, tested against data, and peer-reviewed. But none is exact, final, or absolute. Together, they produce a picture that is robust in its scale and its major features, even if it is delightfully fuzzy in its finest details. That robustness is the point. The value of galaxy counts lies not in the last digit, but in the order of magnitude. Not in whether the number is 1.2 trillion or 1.3 trillion, but in the rock-solid recognition that the universe is extraordinarily, overwhelmingly rich in structured matter. A century ago, the number of known galaxies was effectively zero. A few decades later, it was in the dozens, then the thousands, then the millions. Each leap reflected not a changing cosmos, but a changing view, an improving lens. Today's numbers continue that unbroken trajectory. They tell us that galaxies are not rare, isolated islands. They are the dominant units of visible structure in the cosmos. They fill space, clustering along filaments, crowding groups, swarming in clusters. They populate the void, faint and diffuse. They also tell us something quieter, more philosophical, that the universe does not yield to simple enumeration the way everyday objects do. It resists being totalled up cleanly. Every attempt to count reveals new categories, new edge cases, new subtleties that complicate the picture. In the face of this, precision gracefully gives way to perspective. This shift can feel unsatisfying if what you seek is a single, definitive answer. But it becomes deeply, profoundly satisfying when the goal changes from a childish demand for certainty to a mature appreciation for understanding. The number of galaxies is not a score to be settled. It is a summary of how observation, theory, and limitation intersect. When astronomers revise estimates upward, they are not correcting mistakes so much as incorporating previously unseen structure into the fold. When they quote uncertainty, they are not admitting ignorance so much as respecting the crucial boundary between data and assumption. In this sense, galaxy counts function as a mirror. They reflect the reach of our instruments. They reflect the maturity of our theories. They reflect how carefully we handle what we don't know. They even reflect a philosophical restraint, the decision to stop where the evidence stops. Scale matters more than precision here. Whether the observable universe contains 200 billion or 2 trillion galaxies, the overwhelming implication is the same. The cosmos is populated on a scale that obliterates human intuition. It contains far more structured matter than can be held comfortably in the mind, even when reduced to mere numerals. And yet, those numbers are meaningful. They anchor our imagination to reality. They constrain our wilder models. They remind us, viscerally, that the Milky Way is one among an immense population, not a central fixture or a prototype, but a single example in a sea of diversity. What the number really represents, then, is not an answer to a counting problem, but a statement about abundance under constraint. It says that within the limits of what can be observed, corrected, and responsibly inferred, the universe is lavish with galaxies. It also says that certainty has a boundary, and that science is at its strongest, its most honest, when it marks that boundary clearly, rather than pretending it does not exist. As this discussion draws toward its own horizon, that perspective matters more than any single figure. The question of how many galaxies there are does not resolve into a tidy, conclusive sentence. It resolves into an appreciation of scale, of method, and of limit. And in that resolution, something important happens. The universe becomes neither fully known nor fundamentally mysterious. It becomes intelligible in parts, bounded in others, and forever open to deeper refinement. That balance between knowledge and ignorance, Between confidence and humility, more than any number, is what the grand count ultimately represents. Counting galaxies has never been a task with an end point. From the moment astronomers realized the Milky Way was not alone, the act of counting became inseparable from the act of discovery itself. Each improvement in observation changed not only the number, but the very meaning of the number. What began as a question of how many objects could be seen slowly, inevitably, became a question of how scientific knowledge grows, how it corrects itself, how it builds. Counting, in this grand context, is not bookkeeping. It is an evolving scientific process, a core thread in the story of cosmology. At every stage, galaxy counts have reflected the tools available, the definitions in use, and the assumptions considered reasonable at the time. Early counts were shaped by the naked eye and photographic plates. Later counts depended on digital detectors, statistical surveys, and the first crude simulations. Today's estimates draw on space telescopes, multi-wavelength observatories, and vast cosmological simulations run on supercomputers. At no point has the universe offered a final answer. Instead, it has offered partial views that improve gradually, sometimes unevenly, as our methods advance. What changes is not just how many galaxies we think exist, but how confidently we can describe different parts of the population. The bright giants, the faint dwarfs, the distant infants. This is why revision is not a weakness of galaxy counting. It is its defining strength, its lifeblood. When estimates rise, it does not mean earlier astronomers were careless or mistaken. It means they were working honestly, brilliantly, within the limits of their evidence. As those limits expanded, so did the count. Each revision records progress, not failure. Humility is built into this process. Astronomers are careful to distinguish, in their papers and their talks, between what is observed directly and what is inferred statistically. They separate detectable galaxies from predicted populations. They acknowledge that some systems will always remain below our detection thresholds, while others lie beyond causal reach altogether. This restraint is not pessimism. It is precision. Scientific counting advances by marking its boundaries clearly. It does not blur the line between evidence and extrapolation. It does not claim completion where none exists. There is also a deep, beautiful continuity in this process. Modern galaxy counts, for all their sophistication, still rest on the same basic principle that guided the first pioneers. They begin at home, with the Milky Way. Distances are calibrated locally, using parallax and Cepheid variables. Galaxy types are understood by comparison with our nearest neighbours. The structure and history of the local group inform the models we apply across billions of light years. In this sense, the counting always returns home. Even now, uncertainties in the Milky Way's own mass, its exact extent, the completeness of its satellite population, ripple outward and influence our broadest estimates. The discovery of a new ultra-faint dwarf galaxy orbiting our own still alters our expectations for what might be lurking around other giants. The nearest galaxy remains a reference point, not a solved problem. This circularity is not a flaw. It is a reminder that all knowledge is anchored, perspectival. We do not survey the universe from the outside. We study it from within one galaxy at one moment in time, using signals that arrive late, filtered, and incomplete. Every count, every map, every model carries that embedded perspective with it. Seen this way, galaxy counting becomes less about grand totals and more about the process itself. It is a sustained dialogue between observation and theory. Surveys reveal patterns, models attempt to explain them. Discrepancies prompt refinement, new questions, new ideas. New instruments reopen questions that seemed settled. Numbers shift, not randomly, but in response to improved understanding. There is no expectation that this dialogue will end, that we will someday declare the process finished. Future telescopes will detect fainter galaxies, new wide-field surveys will explore vaster areas with greater sensitivity. Simulations will incorporate more detailed physics, from magnetic fields to the complex chemistry of interstellar gas. Definitions may evolve again as we discover new classes of objects that blur our existing categories. Each step will add complexity, nuance, and wonder, not closure. This openness is not unsettling, it is stabilizing. It ensures that our conclusions remain proportional to our evidence. It prevents numbers from hardening into dogma. It keeps the science alive, responsive, and vibrant, rather than rigid and final. Ending where the story began brings this full circle. The Milky Way still arcs across the night sky as a faint, hazy band of countless stars. It still feels singular, immense, and all-encompassing from our place within it. It still hides parts of itself behind veils of dust, in the glare of its own core, in the dark matter halo that we feel but cannot see. Even here at home, completeness remains out of reach. And yet, from that imperfect, limited, intimate vantage point, astronomers have pieced together a vision of a universe filled with galaxies beyond numbering. Not through certainty, but through the careful, cumulative accretion of evidence. Not through final answers, but through a process that refines itself over time, that learns from its own limits. Counting galaxies, then, is not about pinning down the universe, boxing it up. It is about learning how to ask large questions responsibly. It is about how to revise answers without embarrassment. It is about how to remain grounded, empirical, and humble while dealing with scales that dwarf our intuition. The universe, in this sense, remains unfinished, not because it is incomplete, but because understanding it is an ongoing activity, a journey, not a destination. The numbers will continue to change, the methods will continue to improve. The picture will continue to sharpen at the edges while new, fainter frontiers emerge. What remains constant is the approach, careful observation, explicit limits, a willingness to revise, a deep respect for uncertainty. That is what galaxy counting ultimately represents. Not a final tally of what exists, but a record of how far our understanding has come, and a reminder that even at the scale of the cosmos, knowledge advances one measured, humble, awe-inspiring step at a time. The Milky Way turns quietly within a vast population of galaxies. None of them fully counted, all of them part of a universe that does not demand completion in order to be profoundly, stirringly understood. And in that unfinished, open-ended state, the science remains both perfectly grounded and infinitely open, exactly where it needs to be.